welcome back. Now we have another lecture on physical concentration in our Destination Brazil initiative from Andifs. I welcome you all. And as I mentioned to you before, today we're going to complete our short course on mineral processing with another step, with another set of machines. So now we already took our ore, we brought our ore to our mineral processing plant, and now it's time to work with it because we already grinded, and now we have to separate what we want from what we don't want. Okay, so the idea is now separate the minerals that we can actually sell or put on the market from the minerals that we call it gang minerals. Okay, so we can take a look at many different properties from our material in order to separate them. And I'm gonna show you guys the most important ones today, except for one that is going to be the property used or exploited by flotation. Flotation is going to be the subject of our next lecture, mainly because of its importance nowadays. Over 50% of all commodities on the world are concentrated by flotation, so it's really big and quite important, but also because this presentation it's quite big, so we're gonna save the best for last. Okay, so the first property that we can actually exploit it are optical properties, and definitely we can do this manually. We can just put all our material on the table and just go there and start to looking and separate it, the blues from the yellows and so on. And that's quite common for diamonds, even for other gems like emeralds in Brazil, or even some gold nuggets. You can just go there and pick by hand. Okay, but we know for sure that's going to be extremely expensive, slow, and after a few hours you just can't look at the minerals anymore and you completely ruin your process. So definitely we need to step up and take different measures to deal with this material. Okay, so now I'm gonna show you guys some machines that can do what we call ore sorting. Okay, so ore sorting would be exactly what the name says. We're gonna separate our minerals using one or more properties that we can just take a look at it. And by taking a look, I mean color, for example, or we can, again, improve the process by multi-sensors, just like XRD. We can use X-rays to take a look at the material and take a look at crystalline structure of the material and said, oh, that's something that I want to work more on it. So just separate this from the rest of the flow. Okay, so I think it's better for us just to take a look at this movement, and then we can understand better. And I was talking to Ramon before we start our lectures today about things in Brazil and how slow our reaction time is. And these machines, or this kind of machine, it's been around for decades now. And these machines are improving every single day. As you can see over here, we just have air flows. We just blow away material. And we can do this so fast, as you can see on this video from Autotech, that in the end, you just can't see the particles, but the computer can. Okay? And it can separate everything. We're gonna show you in a few seconds the end of the process. Oh, sorry. It's just paused by itself, I don't know why. But you can see that after a few seconds, our material is completely separated. And as you can see, the process works quite fine for coarse particles. And that's really a game changing. Okay, so how this machine works, how it can separate the yellow one from the reddish one. It just take a look at the material using special cameras. That's one possibility. And again, XRF is another possibility. So since we have this integration with great sensors with our mineral processing plant, then we can definitely do things like that. But nowadays, using artificial intelligence, we can even recognize the size and the morphology of the particles, and then we can separate it even better. Okay, now I'm gonna bring you something from Steiner. and then we're going to show you a video about this, but take a look at this load. We're talking about coarse particles, big chunk of particles, something like centimeters, 2 up to 6 centimeters. So we're not talking about a material that is coming out of the mill. Actually, we're talking about a material that has to go to the grinding first, and then we can pre-concentrate this material. So if you consider the amount of material that we're going just to reduce in our comminution plant, it probably is going to pay itself. Okay, so in this example, 35% of the material was just removed, and we're talking about gold ore. And by doing this, we still had 91% of all gold. So we just lost 90% of the gold, but we reduced the mass up to 35%. So it's huge. Okay, the amount of energy that we're going to save, it's really going to pay off. Okay, so that's the machine. That's the Steinert machine. That's one possibility how we can do this, but take a look at the numbers. Okay, so the head sample has 4.2 GPT, and GPT stands for gram per ton. Okay, and after passing on this machine, it was possible to enhance the material up to 10.8 GPT. So it's quite good concentration. Okay, if you consider flotation, again, it's going to be a different chapter. Okay, we worked last year with gold samples from the north part of Goiás state, and we got the samples with something around 1% GPT on our head samples, and after just one flotation stage, we could reduce the mass just to 1/10 of the feeding, and the grades went up to 13 GPT. Okay, so always consider that flotation is really powerful. Okay, but we can't do flotation on coarse particles like this. Okay, so if I could put things together, then would be the best scenario, and that's why we're proposing this to you. Okay, so just don't look at one machine and say, oh, I just need this one. That's going to be pointless. You just have to look at the machine and say, oh, that's the first one that I'm going to put in my industry, and after that I have this one and this one and this one. So the ideas of ore sorting would be like a pre-concentration before milling, and that's really good. Okay, so when you take a look at the machine like this, at the samples like this, you're gonna probably say, oh, that's the same. I have no difference from one bucket to the others. But when you take a look at the samples like this, then you can see, yes, there are things happening over here. The samples are different from one to another. Okay, and that's what I'm gonna show you guys on this video, and it was shot on Namibia. It's a Namibian gold mine. It's quite beautiful mine, considering in the desert scenario. So it's different. At least for us, it's not very regular to have mines like this. Okay, so as you can see over here, we have a grinder, probably a jaw crusher or something like that. And after that, the material goes straight to the Steinert machine. And what is going to come out of that? Just 2 conveyor belts. Okay, and these 2 conveyor belts can definitely separate what has ore from what doesn't. Okay, and that's the beauty of it, because you're gonna still have another mineral processing plant to take care of your ore, but now you reduce a lot of the mass, so you save a lot of money. Okay, so just 2 machines can operate with all of their production. And as you can see, we're talking about 4 up to 6 centimeter grain size, so coarse particles, and the machine can actually blow these particles away, and the result is really good. So again, just consider this: ore sorting is real. It's been around for decades, and many people are already using it. Why not just to take a look on how it works? Okay, give it a try. Many of these manufacturers can do some test works for you for free. You just have to call them and say, oh, I want to test my material, and if it's okay, I'm going to buy the machine. And they're probably going to be pleased to negotiate with you some tryouts, and then you can see for yourself. Okay, and this video is from Steinert, of course. They are showing that even maintenance, it's quite simple, because it's a very high-tech machine. So it's just like a car, has his own computer, his board computer. It's going to give you all the feedbacks, and it's going pretty much to show you how the machine is working from inside. Okay, so it's quite good. And I handpicked, I sorted this paper to you. It's from Prosemi 2015. For you who doesn't know what is Prosemi, it's a conference held in Chile every year, normally on the second semester of the year, and it's from Guiacamin. It's a group, a Chilean group, and they organize conference on all subjects that you can possibly imagine related with mineral processing, mines, but also they extend this to other areas, even automation and so on. So take a look after this video on Prosemin, and you're gonna be surprised how big it is and how nice it is. It's a very good conference, okay? And since the pandemic, it has been switched to online mode, but you can definitely attend online if you want. So I brought this paper, and this paper is from some authors. Among them, we have a Brazilian, it's Walter Valeri, and Valeri is working in Metsu for many years, and they've been doing a great work over there. And on this paper, they are showing two different possibilities for ore sorting. That would be the number one over here, which is the belt type sorting, just the same one that I showed you before. Okay, so you have your feed coming out from here, you have a camera over here, and the camera just take a look at the material, and definitely could be a CCD camera, but also XRD or so on. If even an infrared camera, if it's suitable for your ore, doesn't matter. Okay, but in the end of the belt, you have the separation. You just blow the material, for example, and then you can sort your material. But then you have this shut type sorter that you have your material falling down, and during this process you just sort the material. Okay, what was the Metsu idea? They have a multi system, you have more than one sensor, and the trajectory of the material is slightly different, and you have the main innovation over here. You have a system that is just going to open and close according to your material. So according to them would be a very nice approach, a different one, patents and so on. But what they also bring together with the paper are more information about ore sorting. And these numbers are quite solid and very nice. For example, if you take a look at the mineral processing plant that is downstream over here, normally you can just connect with cut off grade, okay? Because when you talk about cut-off grade, what is cut-off grade again? Is the grade of our ore that I'm going to look at the ore and said, okay, this is actually ore, send it to the mineral processing plant, or just say, no, that's not ore, it's too poor, I'm going to consider this waste. So pile it up in a different place, okay? We don't have enough ore on it, or my grade is too low, so I can work with this block, just remove it. But if you have a better mineral processing plant or technique, then you can reduce your cutoff grade. And that's huge. Why? If you guys remember, I mentioned to you before that nowadays here in Catalão, we're looking to our horizon of having mines over here for something around 20 years. Okay, so that's our reserve. So if we come with an idea and I can reduce my cutoff grade, then I can have more material around my mines, on the mine surroundings, being fed to the mineral processing plant, and of course profit from that. Okay, and then we can increase what? Of course, one, production, that will be possible, but two, the lifetime span of my mine. So instead of having just 20 years, you can instantly have your mine for 30 years, even 40 years, who knows? Okay, so when we take a look at the cutoff grade by this size of the coin, by this side, then we can start thinking, how can I low down my cutoff grade? Go to the mineral processing plant, because mineral process is going to say to you what is the cutoff grade. Okay, and one thing that is quite impressive is that ore sorting can help you with that. Okay, and I'm going to show you guys why, or at least how these authors point out how. Okay, but definitely we can reduce mining costs in some cases, but we can reduce energy. And by reducing energy consumption, we're cutting off costs on our mineral processing plant. And as I mentioned to you last lecture, we're talking about a lot of costs. Okay, so what else we can do? We can increase feed grade. Okay, but how? How can I increase my feed grade by putting on an ore sorter? By having this pre-concentration right on the first stage of mineral processing. And that's really amazing, okay? So the same authors had this table on their paper, and this paper is talking about ore waste break and even cutoff grade, okay? And they perform some calculations. As you can see on the first rows, you're not gonna have any difference regarding having bulk sorting or ore sorting and doesn't have it. Okay, but when you go to the ore right below, you have mining costings being reduced. Oh, sorry, where's my point? Here, just by a little bit, 0.05%, but definitely we're talking about 5 cents per ton. Okay, and if you consider that you're working 800 tons per hour, okay, and you're talking about 45 hours per day and so on, there's going to be a huge number. This number is going to be considerable, okay? And when we talk about processing cost, then you can see differences, okay? Overhead cost is going to be the same, not going to require more people or things like that. In this case, you don't have any cost with ore sorting. As you can see over here, just 40 cents per ton is not something that is going to make you poor, but nevertheless, it is a cost, okay? But when you talk about the total cost, then we're talking about $3 reduction per ton. And every time that you talk about mines, we're talking about million of tons per year. So yeah, make the math. It's a lot of money. And the cutoff grade was reduced in just 0.05%. Okay, and again, that could also sound like a small number, but then the guys perform this simulation. But really taking a look over here, just imagine a cut in your mind, and you have a cross cut in your mind, and you're taking a look at blocks. Okay, every block represents part of your mind. We love these blocks, and I think that the guys who invented Minecraft, they probably look at this and said, they are all made of blocks. Maybe I can perform like a game made of blocks, and I'm gonna call this Minecraft. And it's exactly what we do. We love to have blocks. So every time that we're talking about geology or mining planning, we're talking about blocks. Okay, so the number inside of the block represents what? The grade, the average grade of the whole block. And as you can see on your left hand side, if we consider that our cutoff grade is 0.25%, then this block, for example, it's waste. This block definitely waste, but this block is going to be also waste. And I have to mine it because below it I have ore. So the green line is going to represent our pit design, okay? And we're gonna have to remove all of those blocks, okay? Some blocks going to mineral processing plant and the other blocks has to be piled up somewhere else. And as you can see, when we shift from the left hand side to the right hand side, we have now the same mine, but now we have different blocks sent to the mineral processing plant. And just for you to take a look, we're talking about something around 102 million tons of total ore to the plant. Okay, and if we take a look at this one, we're talking about 110 million tons. Well, we reduce the amount of material. Yes, we reduce 8 million tons. Okay, but taking a look at the total copper to be sent to the plant for 433 up now to 452. Okay, so yeah, we have gains on that, and that's why we can reduce costs, and that's why this paper is so nice. I strongly recommend you to take a look at this paper. It's very good. Okay, so that would be the first thing that we can exploit: the color, the size, the visual properties of your material, and that's why we call it opticals. Okay, but don't be restricted only to what you can see. We can use XRD also for this. Okay, and now I have this beautiful picture of hematite. Okay, and that's our second property, and I didn't put this property in order to have the poorest property and then in the end the best property. That's not the case, because if that would be the case, then my second had to be changed, switched with the third one, okay? Because magnetic separation, it's really important for us even nowadays. And as you guys are going to be able to see in a few lectures, when we talk about space mining or sorting and magnetic separation, it's going to be mainly the machines that we're going to choose to have up there. So definitely that's going to be something that we have to always take a look on it. So Ramon, you raise your hand, please go ahead. Ask your questions, my friend.
Yes. The machine you showed, you sorted the mineral. So you have to break it and do a special size.
Yes, you still have to have a smaller size than the material run of the mine, definitely. But now we're talking about something around 2 up to 6 centimeters. Okay,
Yeah,
so
okay.
grains. You can actually took these coarse particles in your hands and then analyze it. Okay, so when we talk about other machines, just like this one and the next ones all the next ones that I'm going to show to you, you're probably going to have to have what, milling first and then go into these machines. So yes, ore sorting, you still have some restrictions regarding the size, the particle size, but if you consider gems like diamonds or even gold, ore sorting is something very nice. And second advantage, you can do this dry. Okay, you don't need water. And I'm gonna show you some machines that definitely gonna require you a lot of water to work. Okay,
Okay, thanks.
not at all. If you have any other questions, please just let me know. Okay, so let's see some magnetic properties. Okay, so in here I'm trying to show you guys three different minerals. We have paramagnetic minerals, diamagnetic minerals, and ferromagnetic minerals. Okay, so let's start with the ferromagnetic minerals. That will be these ones over here. And one great example of this class of minerals would be magnetite. Okay, so what we're seeing over here is the applied magnetic field and then the mineral magnetization. So when we apply a short field, we can see that it is high magnetization of the material. The response is really high, but after some increase, we're gonna reach this platform is going to stabilize and is going to remain the same. So I can even increase the magnetic field and we have no response. Okay, and that goes both way, like north or south pole is going to be the same. That's why we have the graphic point to two directions. Okay, if we take a look at chromite, for example, would be paramagnetic, and hematite is also an example, and so on. What we're going to see is like a linear behavior. Okay, so if you increase the magnetic field, you get a response, but on a linear basis. And if you take a look over here, around 500 or even 1000, the magnification over here, it's completely different when you talk this magnetization of the material. We're talking in here at 100, 200, 300, and in here we're talking about 1, 2, 3 kiloamperes per meter. So the response is really different. And when you take a look at diamagnetic material, just like quartz, normally people is gonna look at you and said, oh, quartz doesn't interact with magnetic field. But that's wrong, okay? So when you see that magnetite and chromite, they are attracted to the magnetic field, quartz is going to be repelled by the magnetic field. But the force is so small, and sometimes you can just neglect it. Okay, so you just say, oh, quartz doesn't have any interaction with magnetic field, but that's not correct. Okay, so we could separate our minerals, generally speaking, in these three classes. Okay, so or you have a high response in the magnetic field, a moderate response, or no response, or be, for example, repelled by the magnetic field. And one way to exploit this is this kind of machine. And as you can see over here, I'm gonna bring you a lot of picture from IMSC. And I think their logo is really beautiful and clever because the logo is showing exactly what the machine does. Okay, and what it is, I have a belt. I put my material on top of my belt, and then I have the separation of the material on the point of the belt, on the verge of the belt. And you're going to say, oh, but it was exactly what you showed before. Yes, we have many belt machines based, okay? So we have ore sorting, now magnetic separation, and even electrostatic separation, you can use this kind of belts. But for electrostatic separation, we come back in a few minutes, we use more of this for recycling. Okay, recycling have eddy current separators and they are amazing, okay? But not so much for mineral processing. Maybe in the future we're gonna have advanced in order to tackle this material also. But recycling, it's perfect, okay? So guys, what is going to happen is if I put my material on top of this belt, the belt is moving, so automatically my material has movement on it. By the end of the belt, if nothing happens, the material is just going to flow away and then reach one of its possible destination, okay? Because I have a splitter in the end of the belt. So if the material has any magnetic properties, it's going to be slightly attached to the belt and is going to almost turn around the belt and then it's gonna fall in a different place because of my splitter, okay? So the picture is showing you exactly what's going to happen in this machine. And 30 years ago, 20 years ago, I had to spend a lot of money in order to have this magnetic field on my rods, okay? But that's not the case anymore. Remember that strategic mineral that I showed you before, that strategic group of elements called rare earth elements. Nowadays, I can perform this row, okay? I can make the whole row with a magnetic alloy, and I use rare earth to do this, and I have then a permanent alloy, magnetic alloy, and then I don't need to expend my money on electricity anymore, okay? The row is going to do all the trick by itself and it's going to be free, completely free. And that's amazing because in the beginning I spent a lot of energy in order to have the magnetic field, but also in order to cool down the electric parts of this. Okay, so all the wires are going to produce electricity and I had to spend money in order, they're going to produce heat, sorry, and I have to spend money in order to remove this heat from the process. So yeah, I just threw money away out of the window and that's not the case anymore, okay? So now you can see two different drum separators. One is that separator in the end of the belt, just as I showed you before, but on your right hand side you can see something different. This row is not, this drum, sorry, is not rolling in the end of a conveyor belt. On the opposite, it's just below a chute and you just, or a bin, a silo, you just put your material on top of it and the material is going to fall. And during the fall, you can have the attraction of the material to the drum or not, okay? And on pharmaceutical companies, they like this part of setup because you just put your powder on the top and if you have any kind of contamination, it can go straight to the drum, okay? And I think it was like 15 years ago, I got this funny phone call that the guy called me and said, oh, do you produce iron ore? And I said, yes. I live in an area that everything is around iron ore, so definitely we can do iron ore. Why? Because I want to produce iron ore. I said, okay. And where are you sitting on? What is your mine? And things like that. And he told me, oh, I'm living in Rio de Janeiro. Okay. Because Rio de Janeiro is like 400 kilometers away from Ouro Preto, and we don't have iron ore on Rio de Janeiro. And he told me, yeah, but I need to produce iron ore here in Rio de Janeiro. I said, I've thought to myself, maybe it's something new, something that you don't know about. It's just a new mine coming up. I said, okay, so definitely you can do this. And he looked at me and said, okay, I have 2% of iron, and I want to remove because I have feldspar. And I want to produce ceramics with my feldspar. So that's why I want to produce iron ore. I said, okay, that's not the case. So you don't want to produce iron ore. You want to remove contaminants from your feldspar. I said, yeah, that's what I want to do. And we went straight to magnetic separation. and that worked like a charm. We could take this material with something around 2% of iron ore, but that's enough to contaminate your ceramic, and we reduce to something like zero point 0.0 something. Okay, and just by magnetic separation, because we didn't use this machine exactly. I'm going to show you guys what machines we actually used, but this one, it's also interesting. What is the difference between the machines? You can have difference between the intensity of the magnetic field and also intensity on the magnetic gradient. Okay, so these machines are called LIMS, low intensity magnetic separators. And I brought to you guys this table. It's coming from this book down below. It's from Elle Morgan, and she's a very good geologist. I like her work, and you feel free to follow her on ResearchGate, many others. But here you can see some sulfides, okay? And the box that I put on blue, a bluish box in the end, they're for magnetite and hematite, okay? So just take first look at this, the density of this shoe, okay? Because density is going to be another property that we're gonna take special care about, okay? Because you can definitely separate materials by density. And when you take a look at magnetite and hematite, that's also the same, okay? 5.3 for hematite, we like to round things like 5.3, and 5.2 for magnetite. So it's going to be really, really difficult to separate those two by density. But if you take a look at the susceptibility, and that susceptibility is magnetic susceptibility, that's no comparison. Okay, magnetite, it's completely different from anything that you can imagine. So yeah, go for this. Okay, so go for magnetic separation. But how about sulfides? Okay, if I try to float it barite, definitely can do it. But if I have barite mixed with pyrite, then I can eventually float the both minerals together. Okay, and then I'm gonna put in our next stage this two, and I don't have gold on pyrite, but I definitely can have gold on pyrite, chalcopyrite, and even pyrophorite. How can I separate those? How can I sort sulfides? Take a look at the magnetic susceptibility. Again, pyrrhotite has 3,200 when compared to the other ones that like 0 point something or even 5. And we have galene, and galene is minus 0.03. So it's repelled by the magnetic field. And then you guys are going to say, oh, but galene we can definitely separate by density. Yes, and that's the beauty of it. Okay, so you can, on the first stage, remove pyrrhotite, okay, and then you have your pyrrhotite concentrate. And on the second stage, you can remove galene, and then you can definitely have your lead concentrate, okay? And then you remove almost all of the contaminants. And if you still have like other materials like quartz or something like that, and you want to remove, then why not floatate this galene? But just consider the amount of mass that we're going to reduce just by having two machines that are quite simple, reliable, and that has been around for many, many years, okay? So when I have this kind of talks with people that it's going to be like this: insert more machines in your production line. Normally they look at me and say, this guy is crazy. He doesn't know what he's talking about. Because I don't know who started with this idea. And I know that less is more in many areas, like cuisines and things like that. Decoration, less is actually more. So you have less things, you're gonna have more flavor. Okay, I agree, they're amazing. But if you have more machines in your mineral processing plant, then you can have more concentrate. Okay, so instead of just having one machine, one equipment, and giving all your attention to just one, why not having like 2 or 3, and then you can have better separation. Okay, so just consider this. Oh, but the cost is going to increase. Not exactly true. Okay, that's not exactly true, and I'm gonna try to show you guys during this morning. Okay, but then we have two very beautiful pictures of pyrite and pyrrhotite, and as you can see, they are similar. They're not so closed when you take a look at it, but probably if I try some kind of ore sorting, maybe I can end up having this two being mixed. Okay, And then we need other properties to separate those. And that's why I'm showing you this. So on our left-hand side, we have a table coming from Boyd, and Boyd's a professor in the Colorado School of Mine, and he tried to summarize quartz, rock salt, and things like that. And as you can see, he only went up to the whole table to low magnetic susceptibility. And you can eventually see something like magnetite, humanite, and even peridotite, but it's just to make some contrast. And again, you can see that we have magnetic material or high susceptibility from some materials. It's other minerals completely different. And that's why you can use this property, you can exploit it to separate your material. And even if you take a look at some rocks, okay, so that's why petrology is so important. Take a look at your rock, okay? What kind of rock I have? Oh, I'm talking about acidic volcanic rocks. Probably is going to be in the same level as hematite, okay? No, I'm talking about basalts. So basalts normally have high magnetic susceptibility compared with hematite. So maybe I can separate hematite from basalt by doing this. Okay, granites is going to be quite broad family. It's difficult to make any assumptions right now. You have to take a look, but maybe it's possible. Okay, and sediment is going to be the same. I'm not going to show you guys all of those, but definitely you can separate igneous rocks from some metamorphic rocks and even sedimentary rocks by magnetic separation. So take a look at this. Okay, you have many tables around that you can just take a quick look before. I said, okay, it's showing a window that I can try to exploit, and then you go to your lab and perform some tests. Okay, so again, I just bring back to you the same picture from the beginning of our presentations of this material, and I'm going to show you just a little bit how the material is going to be separated on the tip of our conveyor belt. So you have on it magnetic blocks and non-magnetic blocks. They are all connected together, and then you have a slightly change on the particle trajectory, but that's enough in order to change where your material is going to land on one side or the other of our splitter. Okay, but then let's take a look at our operating costs, and that's very nice. Okay, so one kind of machine that I can have is this one, cross belt. Okay, and I'm going to show you guys how it works in a few minutes. Okay, then I can have induced rows, and then I can have rare earth row and rare earth drum. Okay, and take a look at this just 15 up to 25% of the total operating cost of the cross belt. Okay, so again, it's huge because cross belt, even nowadays, I still have to pay for the magnetic field because I have to use electricity being converted into the magnetic. Okay, and that's going to cost. But in this kind of machine, I don't have to do it, and I don't have to have all my drum made of magnetic material. I just need some blocks. Okay, and I showed you before what a magnetic, a rare earth magnetic can do. It's amazing. Okay, you can slash apples, you can smash iPhones, and so on. So this is actually a real flow sheet from Catalão, from the niobium mine. And again, this mine is run by CMOC Group, and I thank you all CMOC friends for that. And they allowed us to show this great flow chart and even to talk about their material. And take a look at this. We have the material coming from the mine. We have just a sieve first, and the coarse material we send to a jaw crusher, then we sieve it again, and then we came to this machine over here. Okay, this is a magnetic separator, and here's the trick. I don't want the non-magnetic material. Okay, so the magnetic material is directly associated with the rock that's going to be bearing the minerals carrying niobium. So it's quite complicated. No, it's quite simple. We have a rock called nelsonite, and nelsonite is going to bear niobium, and nelsonite has magnetic properties. Okay, so we did this first cut. Okay, and the non-magnetic material, we just throw it away. We don't want it, and those non-magnetic particles are normally composed by silicates. And our study on rare earth materials from Catalão only focus on the carbonated rare earth carbonates. So we couldn't work yet with the silicates. But if you take a look at this pile, it's huge piles of this material nowadays, we do have rare earth elements over there, and they are not magnets, and they are silicates. Okay, so again, it's a completely brand new world that we could exploit it in the future projects. Okay, so instead of taking a look at the carbonates and taking a look at the niobium bearing minerals, I go straight to the waste. Okay, here it is, one possibility. So that's the real machine. So I took this picture in 2015 or 16, I guess, but the machine is the same nowadays. So as you can see, you have the conveyor belt, okay, and after the conveyor changed to turns, we have under it a drum, and this drum it's rolling, and you can actually see the splitter, but you can see over here that it's like a box over here, and this is receiving the material that I don't want it. Okay, I want the magnetic material. So taking a look at a different angle, you can see the splitter right here. That's the splitter. Okay, so everything that falls in here, it's waste or. So as Ramon mentioned to us, is there any particle size distribution that I should take a look at it? So just take a look at the size of this material and this material and so on. Okay, but then again, if I have a huge block, a huge chunk of Nelsonite, I'm probably going to lose this chunk. Okay, because the drum doesn't have magnetic field high enough in order to change the trajectory of this big chunk of material, and I'm going to lose it. Okay, so yeah, we always have to consider that for one particle size, I have one different machine. Okay, it could be even the same machine, but I have to set up the machine for the right particle size distribution. Okay, always like this. So Ramon, yes, you can use the machine, but you have to set the machine up. Okay, it's not only the thing of just go there and use it. Okay, and that's the cross belt separator. I think the GIF is not giving you the very good idea on how this thing works, because that's a quite old cross belt separator, but it's actually working. So you have on the GIF, the animated one, you have one belt, and on the fringe of the belt, on the turning point of the belt, I have a second one installed almost perpendicular and almost 90 degrees of it. Okay, so when it changes and the material is going to fall, the magnetic part will just jump to the other conveyor belt and it stays below the conveyor belt, attached to it because of the magnetic separation, sorry, the magnetic susceptibility, and then I just pull this material out of it. Okay, and in this cross belt separator, it will be slightly different. I have my main belt moving in this direction, for example, and then I have another belt moving in this direction, and that's why we call it cross. Okay, because we're going to make a cross cut. And my magnetic field is going to be produced right here. Okay, so the magnetic material is going to go up and going to attach to this other belt over here, and then these rifles over here, they can just move the material to the side, and then the material is going to land over here, because in this area I don't have magnetic field anymore. Okay, so this machine is quite used a lot on mineral processing plant, but not for ore concentration, actually to remove any kind of contamination from my ore, but contamination brought by the machines or even by the drilling and the transportation and so on. So sometimes you can just see a nut going on top of my material, or even a screw. Okay, and if I let this material goes further on my mineral processing plant, then I'm going to have a lot of problems with grinding, milling, or even on my hydrocyclones, I can end up having a foreign body inside of it. So yeah, remove this material as fast as you can and more efficiently as you can do it. But then again, we don't have yet permanent magnetics that I can use to assemble this machine. I have to use electricity in order to produce the magnetic field, and that's why the cost goes up. Okay, this one is also a different setup of the machine. We still talk about LINS, or LINS, that stands for low intensity magnetic separator. But now we have a wet low intensity magnetic separator. I just showed you guys dry ones. Okay, so how this drum works. Okay, I have on the bottom of it a place like a pot that I can put my slurry on it, and as you can see over here, the slurry is just flowing through this part over here, and then it's going to feed our equipment. And this over here, this barrier over here, is just to change the flow. So in here I have a Reynolds number higher than I have in here. So Reynolds 1 is higher than Reynolds 2. So I go from a turbulent flow into a laminar flow, and then I just feed our equipment. And then the material goes below the drum, and then the magnetic ones is going to exit out and up together with the rotation of the drum. Okay, so if we take a look at this Mexu video, maybe we can understand a little bit better our wet limbs. Okay, it's going to show you how it works from inside. So you can see slurry feed, the tailings, the concentrate, and how this machine works. Take a look at the rotation of the drum. Okay, it's quite important to take a look at the drum rotation. So let's see it from inside. The slurry is going to be fed. It's going to be accessing the equipment from below, and as you can see, we have permanent magnets installed inside of the row. Okay, and to the right hand side we're going to have our magnetic concentrate, and on the left hand side we're going to have our non-magnetic material exit the machine, and it works quite good. And we can even assemble more than one. Okay, it's quite regular to have an assemble of all of this material. So when we have these machines associated like that, I can even feed one, okay, the second, and feeding the third. And then what we're going to have in here, it's parallel machines working together. Okay, so the material that is going to be the drum number 1 never gonna change to drum number 2 or to drum number 3. Okay, they are completely isolated one from another. Okay, so this is one possible setup. Okay, but that's not the thing that I want to show you now. I want you guys to consider, just consider for a second, that my material, my feed, is going to enter the system in here. Okay, and the non-magnetic is going to come down in here, and then it's going to move to this one. Okay, and then it's going to move in here and to this one. Okay, and after all of this, it's going to exit the machine right here. Okay, this is also one possibility, but that's nothing. That's not what is happening over here. What is happening over here, it's actually something like this. Okay, I can have our magnetic concentrate coming from this machine to this one. Okay, so now we're talking about magnetic particles, and again from this machine to this one, and that's the magnetic particles, and from this machine up to this. Okay, so the idea in here is to have a rougher separation over here. Then I have a cleaner just to remove the gangue minerals that went with the rougher concentrate, and then I have in here a re-cleaner machine. So by doing this, definitely I'm gonna have more of my ore and tailings, but in here I'm gonna have a very, very rich final concentrate. Okay, and that's my main goal. So take a look at this and get used to know that we can have the same machine but doing different cuts of our material: rougher, cleaner, scavenger, and even re-cleaner. Okay, I'm gonna come back to these circuits later on with you, but it's really important that you guys understand that I can assemble circuits. Okay, so don't consider that like grinding, I'm gonna have just one equipment, the material goes in, out, and so on. Okay, and I'm not gonna have circulating load. That's not the case. Okay? After milling, everything is going to be about circuits. Okay, and I'm gonna have to prepare those circuits in order to increase grade, increase recoveries, and so on. So what is recovery? What is its name? I'm going to show you guys in the future how to make all of those math. Okay, so this is a footage for MagQuip, and these guys produce, among other machines, magnetic separators. especially drum magnetic separators. And as you can see, from time to time, you can even see some material attached to the drum. The drum is turning, the material is still attached. So this is the magnetic part of the material exit the drum. And when I take a look on the different views, then I can see how the machine works. And it's a big machine, but not a giant machine or anything like that. Okay, so that's the magnetic material leaving the machine. As you can see, it's completely different from the right hand side with the left hand side. The material even exits the machine with less water than what the slurry was fed to the machine. Okay, in here you can see two working together, and again, it's really good machine. And we have those also here in Catalão. As you can see, the label, so magnetic wet drum separator. What is not showing over there, that is a LIMS, low intensity magnetic separator. So again, pictures from Catalão, but those pictures are not from niobium, but actually from the phosphate plant. Okay, and on the phosphate plant we have two different magnetic separators. That's the first one, low intensity magnetic separator, and we installed this machine together with the mill. So the material goes to the mill once. After the material exits the mill, it goes straight to the magnetic separation, and then we can remove magnetite and big part of the magnetic particles. Okay, so we're talking about iron ore particles. Sorry, iron particles, not ore. Let's take the ore out. So iron particles. And in the end, we're gonna do another magnetic separation, but now with our final concentrate. And I come back to that in a few slides. Okay, so that's the flow chart of one of the plants that we have, but this one also back to niobium. So those plants over here are actually this plant in here. Okay, so we have two, 47 and 76. So I'm showing you guys one picture, for example, of the 47, this one. Okay, so what I'm seeing right here, I'm gonna take the tailings from these two plants, and we're talking about 150 tons per hour with something around 0.67% of niobium. And I'm going to pass this material through hydrocyclones, magnetic concentrator, and then I'm going to mill the material again, and goes to flotation stage, silica flotation followed by niobium flotation, and in the end we have something like 0.67 tons per hour. So let's just consider again in here 150, and I'm going to produce 0.67 tons per hour. So that's the amount of material that you're going to take out of this flow. Okay, but in here we have 0.67% of niobium, and here we have something around 44%. Okay, it's quite good. And we're not talking about only niobium, this is actually Nb2O5, niobium pentoxide, and that's why 44%, it's really high grade. Okay, and how we can do this? By magnetic concentrators. You can see here and also in here. So magnetic separation is still quite important for us. And now we're taking a look in order to produce not only niobium, not only rare earth, but also titanium. We do have titanium on this material, and now we're trying to take the final tailings and go straight to another magnetic separation, and then we can probably recover ilmenite. Okay, and then we can produce titanium. Well, this is the machine that I like most. Some people call this Jones magnetic separator. Other authors are going to call it carousel magnetic separator because it's like a carousel and it works the same way. But some other authors can also call this wet high intensity magnetic separator. Okay, so this is a machine family, but people also related this one with this anagram. Okay, so wet high intensity magnetic separator. How this machine works? You have two poles, and in here it's not quite visible to us, the poles, but you have two poles, and in this picture you can see north and south, And I'm going to feed my slurry in one place right here, at the beginning of the pole. So during this movement, everything in here is turning on this direction. I'm gonna have material, the magnetic material, get attached to this matrix. So those slots over here, they are not actually slots, they are magnetic matrix. And when I'm leaving the magnetic field, I add water on this point, and then I wash away the middlings. Okay, what are the middlings again? They are the material that got attached to the matrix, okay, but they are not so high grade like those ones that remains on the matrix after I cleaned it, after I wash it. Okay, and how about the non-magnetic particles? They go straight down when you're on this section over here. Okay, and I have a video to show you guys. It's going to be easier for you to understand. Okay, but let's just take a look at this picture also coming from Metsu. Okay, and we have an extra information over here. Guys, the problem with this machine is the matrix has to be clean. Okay, you have to clean your matrix. First problem. Second problem, I don't want magnetic hysteresis on our matrix. What it is this? Any kind of magnetic field remaining after this magnetic stage, after passing through my coils. Okay, so when I pass through my coil, I'm going to convert electricity into magnetic field. Okay, but after exiting the coil, I want the material go straight down. Okay, if it's not magnetic, it's going to be removed first. If it is magnetic, just after the finish of the coil. Okay, but that's not the case, because the matrix is going to remain with some magnetism on it. Okay, and that's why I have to do something in order to clean the matrix. Otherwise, it's going to be completely clogged, and I'm going to stop working. Okay, so Metsu come with a very interesting idea. They flush water, but not from the top to the bottom, but on this case from the bottom to the top. Okay, and you even remove some magnetic particles. Other manufacturers, they do this by blowing compressed air. So you can choose. Okay, but that's the thing. I'm gonna put my rinse water over here, and also I'm gonna feed the material in this position. Okay, I'm going to recover the non-magnetic particles on this sector over here, because that's the sector where I had my coil. And after leaving over here, the ring is turning this way. Okay, I'm going to have an area that I'm going to recover the magnetic particles. So that's another footage from Catalan. As you can see, our material ore is quite brownish or yellowish one, and that's apatite. Okay, that's our phosphate rock final concentrate. Okay, what are you seeing over here is the water cleaning the matrix. So those guys over here, those are the matrix. Okay, that's the magnetic matrix over here, because this machine is turning like this. So in here, I'm feeding the machine. Okay, that's the pole. The pole is going to be right here. And as you can see, I have, for example, a north pole in here and a south pole in here. So this machine operates this one with just 2 poles, but I could easily adapt another pole in here and another pole in here, and then I have a 4 poles machine. And in Brazil, we have a company called Gauss Tech, and here I send some regards to Gauss Tech and Pancracio and his team. And he could develop, this guy Pancracio, he could develop a machine with 64 poles. 64. Okay, it's quite impressive, because you increase a lot the machine productivity without increase its area. It's the same machine, but with a lot of poles. So many poles working together, you can increase abruptly this massive increase in your throughput. Okay, so very, very good machine. And this video is from Gauss Tech and All Mineral. These 2 companies went together here in Brazil, and that's why you can see All Mineral is a Deutsche company, I guess, and Gauss Tech, it's a Brazilian company. That's why they are red and green. So in here we can see that we have 1 rotor, 2 discs, 2 carousels, and I have 2 poles per carousel. Okay, and you can see clearly 1 slurry from different color from the other point. That is going to be our middlings. and also the non-magnetic material, and after that the magnetic material. But let's zoom in and see this better. Okay, so the first movement that you see over there, the first pipe is the feed, the second pipe is just water to be clean, to clean our matrix and remove the middlings, and the last water is going to be added to remove the magnetic particles. And as you can see by the colors below, you have something like quartz exit just in the beginning of the equipment. That's the feed, and below it the non-magnetic particles, the quartz, and then we have the middlings, and then we have the magnetic concentrate. Where I can use this machine, iron ore for example. If I feed this machine with iron ore, instantly I have tailings, then I have middlings, and these middlings are carrying iron ore, so iron particles. That's why I'm gonna use flotation on this flow, okay? But the last flow, that's magnetic concentrated, okay? That's ready to be marketed, and that's why I'm gonna take this last material right over here and just sell it as a final concentrate, okay? So I'm really good to go just with this machine. And this machine is allowing nowadays many companies in Minas Gerais to reclaim their tailing dams and to send the material from the tailing dams straight to this machine and to recover iron ore on a high grade basis. Okay, so I want to show you guys some lab equipment, and I got access to this lab equipment on the Clausthal Technical University, and I send my regards to all my colleagues on TU Clausthal, especially Professor Daniel Goldman from the IFAD, who was my supervisor during my postdoc for 1 year in Clausthal, and also Tobias Elvert. And what I'm seeing over here is the Jones magnetic separator. And again, the name Jones. Why we only talk about Jones? Because he was, and his company, one of the main manufacturers. And we have many different layouts for this, okay? But the magnetic matrix that I showed you guys before, it's right here. So this is the matrix, and that's the gap on the matrix. And one thing important for you is take a look at this. Know for sure how big or how small it's the gap. So this in here is this one, and we have a gap of 0.8 millimeters. And why this is important for me? First of all, because you can only add a particle in here that is smaller than your gap, and of course we know this, but then we come with this relation. Okay, if I take the coarse particle that I have, and if I measure it, and I have a diameter of d, this d has to be related with this d over here, and this d is the gap, something like this. The d from the gap has to be higher than 3 times the size of the bigger particle that I have. Okay, so if I have a gap of something like 0.9 millimeters, the bigger or the coarser particle that I have to add on it has to be like 0.3 millimeters. Okay, if you try to do more than this, probably your particle is going to clog. And another thing important regarding matrix, because I have different kind of matrix, like steel balls, steel wires, or even like steel cloth I can add inside of this machine. Okay, in this case, the magnetic line over here, the magnetic field is going to be convergent. So I have one pole in here and another pole in here, and I have what I call the power of the tip, because I have a convergent magnetic field over here, and this increase a lot my magnetic field. Okay, so always try to use matrix like this, and you're gonna have a very good result. So if I took that first machine, the first lab machine, the Jones magnetic separator, and put it in a not batch equipment, not batch process, but like a continuous process, I'm gonna end up with this equipment, also call it Jones magnetic separator. They're both wet, but this one is a wet high intensity magnetic separator. Okay, as you can see over here, I have a pole in here and another one in here. I feed my material on one side, I wash it on the other side, and yes, it's the same equipment that I showed you guys before, but this one comes from MBE, and it's a Jones magnetic separator It's quite good, okay? As you can see over here, that's their logo, MBE, another Deutsche company. But this guy over here, it's normally the favorite one when we talk about lab, okay? So this is called not Jones again, but Frantz magnetic separator. And how it works, I add material in here, okay? And this is my feeder. So the material is going to come out of it into this inclined plane over here, and I have actually two different angles. I have this angle over here with the horizontal, but I also have an angle from this side to this side. So the shut, it's like this, but it goes up like this. So I have one angle in here and another angle in here, okay? And these coils over here are going to produce the magnetic field, and then I have material going to one spot in here, and the material goes to another box in here, and I definitely can separate the material. But that's going to take us hours and hours just to do a sample like 10 grams or 20 grams. Why? Well, first you can and you have to change both angles, okay? That's the first thing. Second thing that you have to do is you have to change the magnetic field. So you have 3 variables that you have to set up, and that's going to take you a lot of time, definitely. But the machine works quite nice. It has been produced for over 80 years. We have a French company, and this French company produced this machine for over 80 years. It's been around for a while, right? So let's go to electrostatic separation and let's see how this works and how this can actually separate minerals. Well, theoretically, we could use this as a universal method to concentrate minerals because all minerals, they have affinity or not with the electric fields, so it could be used, okay? But actually, that's not the case. First of all, because of water, we have to remove water as much as we can. Water really is going to damage my process, and because of the electric consumption, okay? So if you had like infinite electricity and if you didn't have water, then that would be the main way to separate minerals. So wait a minute, that's exactly what's going to happen in space, okay? So in space we don't have water, at least we don't have a lot of water. Probably going to have solid water but not liquid one, and we could have infinite amount of electricity around us, or it could exactly produce this, okay? So yeah, that's the way to do it when we talk about space mining, okay? But we're going to come back to space mining in the future, and then we're going to discuss everything that we learned in these lectures on space mining, okay? That would be like the way to close everything that we learned, okay? But we still have some very restricted and narrow applications in our planet for electrostatic separations, okay? I'm going to try to show you some of those, okay? But it's going to be like a brief presentation as I did before. Again, the most interesting in here is to remove water. So if you're in a situation that you don't have water, you have to go for a dry separation. Of course, you can consider ore sorting if it's possible. Then you can consider magnetic separation, and then you can think about electrostatic separation. So guys, consider this. We have now many other information that we had before. Before today, we only knew how to break things down. Okay, now we know how to separate, and we know that for sure we can use how they look, how they respond to a magnet, how they respond to electrostatic field, and then we're going to see a little bit more in a few minutes, okay? But every time we have to consider this. What is the particle size, okay? And do I have water or not? That's the main things that we have to consider. So in this case, we don't want water, we don't want it at all. So if you live in an area that you have a lot of water or rainwater, then you shouldn't consider to use this kind of equipment, because you're gonna spend a lot of money, not only to produce the electrostatic charge in your material, but also in order to dry your material, okay? And that's why you should consider to move away from this technique. But nevertheless, we're gonna talk again about the drum, okay? And I'm gonna feed the material on the top of the drum, and then we have an electrode, and this electrode works with the corona effect, and I'm gonna try to charge our material, just bombing it with electric charge, and then we're gonna have another electrode and that's going to be represented by this HV, high voltage, and it's a positive voltage, okay? And then we have deflection of our material. So the material that is going to be collected is going to be higher to the right, then we're going to have the mixed material and the smaller particles in the middle, and then the material who gets attached to the drum coming on the other part, okay? And then I have one last electrode in order to remove any kind of electric field that is remaining on our materials. And then if that's the case, I can actually add a scraper or some brushes in order to remove material that stick together with my drum, okay? Another thing that we can actually do is to use a free fall type of electrostatic separator. And in this case, I just let the material going from the top to the bottom just by free fall, and I have charged plates around it. So if material migrate from the center to the plates, then I can separate the positive from the negative ones. Okay. Also a possibility. And this is the standard machine that we use on our lab. And I tried to separate my rare earth on this machine, and I completely failed to do this because, as you can see over here, I supposed to have 3 products, and all of those 3 products in the base of the equipment, on the lower part of the equipment, and then I have this feeder right here on the top. I can adjust the angle of these 2 electrodes, and that's what you're seeing over here, the corona electrodes in here, and then the second electrode over here. And when my material enter this and start to go in here, it was so fine particles and so strange particles that when they got in touch with this electrodes cloud over here, it just flew backwards to this side. So instead of having my material coming to these 3 places, I had all of my material flowing away in this direction. And it was quite strange because I looked to the machine and then I looked to the wall on the side of the machine, and everything was getting stuck on the wall. So yeah, I failed miserably when I tried to use my carbon concentrate, my rare earth bearing minerals in this machine. Why? Probably because of the particle size. Okay, they were too fine to use on this machine. So everything that I showed to you guys up to now, we still have this particle size limitation. If the particle is too small, you just can't use it. Okay, and there are some theories and some calculations that you can actually perform in order to try to evaluate if you're going to have a good separation or not in this kind of equipment. Almost all of them, you can just go online and take the equations and input some pretty preliminary data, and you can have a glimpse if you're going to succeed or not using this equipment. And I failed. Okay, it doesn't work at all to find particles, but nevertheless, here is the equipment. And so this is a table and some pictures coming from the Wills and Finch book, that Wills Mineral Processing book that I showed you guys on the last lecture. And it's one of the most significant books for mineral processing. And the assemble is the same, okay? But then you can see some material that are going to be pined to the drum, and some material that is not going to be pined on the drum. And as you can see over here, we have apatite as being one of the minerals that is going to be connected, pined to our drum. That's going to be the non-conductors. And if you take a look over here, we have magnetite as a material that is going to be thrown away. Okay, there is a conductor, and that could be one hell of way, because we have hematite also, to separate the apatite, the phosphate rock, from the iron bearing minerals here in Catalão. Oh, it's going to work, it's going to be beautiful. Yeah, but here's the catch. We have something like from 8 up to 12% humidity or moisture in our material, and then you just can't use this kind of equipment. Okay, and then we have the problem of the particle size. If I try to use this equipment with coarser particles, then I have mixed particles, and then I don't have the response that I want. If I try to grind down the material and mill it, then I have particles too fine that I can't use the equipment anymore. So that's the situation that I have to tackle with. If I try to concentrate coarse particles, I end up having mixed particles. If I try to increase the liberation of the particles, then I end up having fine particles. Then I have to find the missing link, or I have to find a particle size that we can actually use these machines, or I can go straight to the fine particles and develop new machines. Okay. Nowadays, what people are doing, flotation, 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 flotation. So our discipline is about challenge in mineral processing. So one challenge, water. Second challenge, water quality. So let's come back to the first, water availability. Second, water quality. Third, electricity. Okay, so we need better ways to deliver power to our mineral processing plant. So 3, power. 4, particle size distribution or fine particles. Okay, so everywhere and everybody around the world, we're considering now what? Deal with fine particles. So if you have a way, if you discover a way, a new property, something that can allow me to work with fine particles, then you're gonna get like a Nobel Prize, okay? Because that's the way to do it. We need, as fast as we can, to find a way to deal with fine and ultra fine particles. We don't have those machines yet, okay? And everybody is just seeking for those. And if you come up, with this technology, it would be a so game changer that's going to allow us to reclaim almost all tailings dam around the world. Okay, and I mean European ones, Chinese ones, Canadian ones, Brazilian ones, and so on. Okay, because our problem is we still have grades, considerable grades on our tailing dams, but we don't have technology to recover them. Okay. So yeah, guys, if you want to make a PhD and if you're really, really clever, first of all, and curious, brave, go to fine particles concentration. Why brave? Because you can end up like 3 years later with no PhD at all. Because probably you can try a lot of things and you can fail on all of those. Okay. Many people have failed until now. But you know what is the beautiful thing about the impossible? Something is impossible until someone gets there and do it. Then it's not impossible anymore. So it's impossible now because nobody has done it before. But as soon as someone, just one person do it, it's not impossible anymore. Okay? So use your inspiration, use your clever, your ability, and try to come out with different ideas. One thing is quite good. Okay? Now we have lasers on our cell phones. We have LiDAR on iPhones. Maybe LiDAR is going to change mineral processing. Maybe not. Maybe it's going to be X-rays. Maybe not. Nevertheless, we need to find a way to deal with fine particles. Okay? The laws of physics get a little bit fuzzy when you talk about fine particles. If you have time, I can talk with you about this and even show you some results about this. But segregation, stratification, everything changes when you move into fine particles. When you move into particles below 10 micrometers and into nanoparticles. And that's the future. Definitely that's the future. Everything now that is quite technological comes with the name like nano or quantum. Now this is quantum technology, and normally it's not related with quantum world at all. And normally it's wrong definitions about what is quantum mechanics, but nevertheless, the nano name, a nano prefix, it's now something trendy. Everybody wants to have nano something, okay? And yes, it's a lot of money, and the money is still over there. The capabilities of the companies are still there. The people are there, and we need to process this material, okay? So guys, help us to find out a way to deal with this machine, this particles, okay? So I'm gonna show you another electrostatic separator, and this company, JXSC, I didn't know this company before. I think it's a Turkish company, I guess, and they have plenty of different equipments, okay? And this electrostatic separator from them are quite nice because you have this separation happening around all the equipment and not only in one part of it. And you can even have like cleaner and recleaner separation in the same machine, okay? And I was impressed when I went to Turkey for the first time in 2012, and I was really impressed by the cuisine, the culture, and everything. But also to know that Turkish was considerably new to minings. Okay, they had mines for many years, but they were starting industrial mines over there, the industrial engineering, so to speaking. And after those years, I have been back to Turkey almost every year, sometimes even twice per year. And it's impressive how fast they are developing equipments and techniques and everything. And they have very good universities over there. I here send my best regards to my colleagues in the Turkish universities. And yeah, chromite equals Turkey. And it's quite nice the work they're being doing over there. And now the machines there were produced over there. Okay. So guys, with this flow sheet, it's a regular flow sheet when you talk about gravitic separation and physical separation. And the name of the lecture, physical separation, is because we're not going to have any chemical involved. Okay, so everything is going to be physical. It's composed by what? Like gravitic separation followed by magnetic and or electrostatic separation. Okay, and in this case we're talking about iron ore. So probably this Cliff Washbush place, they had some restrictions about water quality, or even with flotation, or they were working with an old company, an old mineral processing plant. We had processing plants exactly like that, except for the green area in Brazil, working with iron ore too, but we removed this kind of route around the 90s, beginning of the 20s, and the beginning, of the 2000s. And why? Because of the consumption of electricity. Okay, and now I think we have everything that we need to come back to this. Okay, and as a matter of fact, we are coming back to this. So the first stage, marked in here by red dots, is the gravitic separation, and in this case they choose spiral as the main concentrator. I'm going to show you spiral concentrator in a few seconds. And then the material goes to the hydrocyclones, and then it feeds the magnetic circuit. So take a look, we have the low intensity magnetic separator, but we have also the high intensity magnetic separator all together. Okay, and on the other side we have the green area where we have high tension circuit, and as you can imagine, we use a lots and lots of electricity. Okay, but then we can produce iron ore, and it could be seen as a standard iron ore procedure. Yes, we could use something like that, but flotation, it's way better, way simpler, and you can have higher grades, high recovers, and so on. So why we should take a look at this again? Because you're not going to be able to perform flotation in space, man. That's impossible. So flotation is something that you can't do on a planet. Okay, you can't do flotation in space. Even in our planet, there are some places that we can do flotation, where high altitude. Okay, so if you go to the Andes, for example, Peru or Chile, and you try to perform flotation like 5,000 meters high, you just can't do this. The bubbles are not going to work as you expected. So you have to take your material, all your material down the hill, and then you can perform flotation. So it's crazy because they are using seawater. Okay, so they take the seawater from the 0 meter high then and pump the water up, but on the other hand they have to take the material that is quite high and bring it down in order to meet the water going up. And then you have mineral processing, and then you pump down your concentrate and also in some cases your tailings. Why not go to something only dry, specifically dry? I don't know, but that's the main route they're doing right now for copper and molybdenum. Okay, it is what it is. They are doing lemonade with the lemons that the life gave to them. Okay, so let's talk about density separation, and this picture quite captured the moment. Okay, so if you have 3 different minerals and you put these minerals in a way that you can have a separation regarding how they interact with your media, then maybe I can exploit this in my favor. In this case, for example, I have wood and I have another different kind of sponge, and sponge and wood are going to float. Okay, and yes, it's the same word that I'm going to use for flotation. Okay, but it's going to float, and the other one is going to sink, and that's the name that we're going to have to use for this kind of technology. So I have sink material and I have floated material, and then I can separate both. Okay, and that goes to many minerals also. And the first picture that I want to show, I think it's a very beautiful picture, is this one, and that's the spiral concentrator that I was talking about, and now I want to show you. And I have two main different spiral concentrators around the world nowadays. We have one called Mark, and we have Mark 1, Mark 2, Mark 3, like Ironman suits. And the Mark spiral is exactly this one, okay? And then we have another one called Humphreys. And I'm gonna try to show the difference between Mark and Humphreys with some pictures, and I think it's going to be more clear to you if I just keep going a little bit for now. But this is a Mark spiral concentrator, okay? And when I saw those guys' website, Voltotech, and I was so impressed that I think to myself, let's print the screen, let's print it, and let's show this to my students, because look at the logo. Spiral Test Rig solves separation challenge. It's quite ambitious, but they are saying that they can solve problem, okay? And they are actually right for some situation. They can solve some problems, not all of our problems, but definitely they can solve some of our problems, okay? And again, this is old school, this is old tech, okay? And for many years, people are looking at this, looking down at this and say, oh, no, I don't want this. But nowadays we have new materials, we have better understanding, okay? But then we need water supply, okay? For this kind of machine, we do not consider about water quality, not as we consider this quality for flotation. So we can use better water, okay, for flotation, but we cannot use like recycling water or used water, processed water, too many times in flotation. In here, we don't have this limitation. You can virtually use the same water forever. You just have to recover it and use it again and recover it and use it again, okay? But nevertheless, let's see how this equipment works. So it's quite simple. The slurry is going to go down, spiraling our equipment, and by doing this, we're exchanging potential energy into kinetic energy, and then we have the separation of our minerals in this spiral. Okay, what is going to happen is the material has high density is going to be close to the center of the equipment, to the, in this picture, right hand side. Okay, so it comes into the middle. It doesn't suffer too much with the velocity, with this tangential velocity fields that are into it. But if you take a look at the material with low density, it's the opposite. It's going to shoot straight up and out of our equipment. So in the end, you have two different zones. One zone with high density mineral and another zone with low density mineral. So boom, that's what you need to separate those, okay? And if we take a look at this, again, JXSC video, it can show you that you can have actually a pile of spirals all together, and that's why you can increase your productivity. And in this case, is also a Mark spiral, and then we're gonna talk why we have a Mark and a Humphrey. The difference is the Humphrey spiral is gonna have ducts, small pipes connected to it along all the height. So you're going to be removing your concentrate, your heavy minerals along all the spiral, okay? And then if you have material going out of the spiral, you have to put water back into the spiral. So you have one, material coming out of the spiral along all the spiral height, and two, more water added to the spiral. But in those kind of spirals, Mark spiral, invented in Australia, you don't have this, okay? So all your material goes in on the top, and all of your material without extra water goes out in the bottom, okay? And in the base of the equipment, what do you have? Like three different routes, three different tubes that you can collect concentrate, middlings, and then tailings. Okay, so you require less water, and you can have for some material better concentration. Okay, this other video is going to show you. I think it's a bad video. I was even in doubt if I should show you guys this or not, but this is mineral processing and it is. Okay, so I'm going to show you guys like bad mineral processing also. Okay, so as you can see, you can't see anything, you just see slurry flowing down. Okay, but that's a spiral concentrator. Okay, and in the end you see this splitter, and then in the you can see the heavy minerals inside and the light minerals outside. And from my point of view, I can actually see any difference between this so-called concentrate. For me, it looks like hematite, so could be iron ore, and this tailing. For me, exactly the same. Nevertheless, according to those guys, they are actually having concentration. So yeah, we're gonna see this as mineral processing. But one thing that I think it's quite good from this video is this. Oh, sorry. Is this moment right here. So it's quite common if you go to a mineral processing lab that you have this kind of graffiti on the walls. So if you're working in a mineral processing lab and you don't have minerals on your wall, you're not doing this right. So definitely you're gonna have your walls repainted like that. And all of my walls are nowadays like this because it's a hydrocyclone that went nuts and then everything splashes on the wall, or it's another machine that just started throwing everything up. And yes, you're gonna end up having walls repainted like that, and that's mineral processing, guys. You're gonna do something like that, but please don't do mineral process on your shorts like this. Okay, so try not to do this. And this guy he's listening to music while he's doing mineral process, so avoid this kind of things, okay, and you're gonna be good. But that's a good video, okay? And I think with this video, we can actually see how the spiral works. So I'm gonna pause the video. Oh, sorry. The idea was to pause the video. I eventually did it in here. And you can see that you have a different color in here than in here. So definitely you're having some kind of ore sorting in here or separation in here. And this hose over here, it's putting water back in the system. Okay, so this is a Humphrey spiral concentrator, and when you add water in here, this water is going to pull the material also in this direction. Okay, so let me just play the video again, but without my marks. Let me just remove it 1 second, and then we can watch the video properly. Okay, and then you're gonna see the slurry going out of the machine in the end. Okay, and then you can see that we actually have some sort of concentration. Okay, so you can see the water going in. So as much turns that you have, better is going to be your process, or at least we hope so. And now you can see that heavy minerals are inside and light minerals are standing outside. They tend to be outside on the outer part. So we're almost in the end. And this duct over here, this pipe that you have over here, it's going to collect all of the concentrate along the way down. And in the end, you have just that box. Let me try to forward here. Oh, sorry. And you can see the difference in color. Okay. So I'm not sure if I'm gonna be able to pause it where it actually shows you the two products. Yeah, let's leave like that. Okay. So let's move forward to another equipment, also old school, also very nice, very used. A lot of people still use this nowadays. For if you go to chromite, like I did in Albania or in Turkey, you're gonna see a lot of those. That's the shaker or shaking table. Both names are correct. And also you can see Wilfley table or Wilfley shaker table because it was developed by these guys. And it was developed initially for gold and works perfectly for gold. Okay, so how this machine works, it's a beautiful machine. We have some pictures like this, then you can have a better understand. So I'm going to feed my material over here in this small area in here, and in this case this is a almost lab scale equipment. You produce your slurry right over here. Okay, so the slurry is going to enter the equipment in here, and this table, it's called a shaking table because it's moving left and right all the time, so it's literally shaking. Okay, and the material is going to move in two directions, and the direction of the movement in our picture from the right to the left, and also from the top to the bottom. Why? Because we have an inclination in this way, like an alpha over here, but we have also an inclination in here, like a theta. Okay, and then on theta we have also the movement of the table, and then the separation starts to happen, and you can see in here the heavy minerals. And when you take a look at this bad boy working with gold, it's quite nice because everything would be like gold particles, nuggets of gold rolling down over the hill, and it's really beautiful. Okay, so you have different products on this area, okay, up to this area, and even into this corner over here. So you can have product in here, here, and also here. In this case, they have 4 buckets because they are considering only 4 products. But one thing important is, if you don't take actions, all of your water is going, or at least is going to try to flow to this first bucket in here. And you can see this. Look at the water level in here, the first one, on the second one, and on the third one. Okay, you don't have so much water when you're moving to the other buckets. Okay, so that's why you have this pipe over here. You feed more water into your machine in order first to lubricate your machine, because it's going to be dry in some places, but also to allow the machine to work properly. Okay, without the water you don't have concentration. Okay, and this machine, I think it's quite clever because there are plenty other machines, older machines, that I'm not going to show you. Okay, like for example, machines that you just let your minerals going down like slice, and if you put a carpet on the bottom of it, you can have like entrapment of the gold in your carpet, and people just look at that and say, oh, okay, I can do something better, I can design a machine, and here you are. Okay, and I was able to visit a plant in Germany for recycling. Okay, for recycling, and the guys are using shaker tables. Okay, and it was quite nice because the plastics, they going to align with the water, and you have plastics over here, a lot of plastics. And when you move on the shaker table, you're gonna see like aluminum going out over here, and then iron or steel coming out over here. It was working perfectly, and it's quite nice. Okay, so that's the shaking table working. It's a GIF animation, and you can see that in here the material looks different from here and from here, but this line over here, that's the line that we need to see. Okay, that's the heavy minerals line, and it's quite beautiful. Again, if it's gold, it's impressive. You can look and say, wow, it's really catchy. Okay, so we have a picture from the paper, and this paper also important paper. Oh, let me just say you guys something that I forgot when I mentioned the first time the Wheels book. So Barry, he's not only the main editor and author of this book, but he's also the editor chief of a very important journal on mineral processing. He's the editor chief of Minerals Engineering. Okay, so if you want to publish a paper, a high impact paper on mineral processing, you're going to have to talk eventually with Barry, because he's the editor chief of Minerals Engineering. Okay, so almost everything passes on his hand. And that's another view of the shaker table. And as you can see over here, the tailings is going to go out in here. Then you have the middlings over here, and you have the concentrate over here. And then they are starting to use this word launder, because people are starting to consider that you actually doing laundry. And then we're going to see some baths and things like that. This name is going to appear in the future. But yes, we're actually washing our mineral. And that's why sometimes you came up with something like screw washers and names like that. Okay, people are so creative. And that's the with a shaker table working also. And this this video is okay, I guess. The quality is not too high. I couldn't find anyone better. But this is also lab scale. As you can see over there, we have a feeder. The feeder goes to deliver the mineral particles. I know the quality is too low, but nevertheless, it's going to feed into that pot. And then you can see, take a look how beautiful it is, the concentrate line. Okay? And that's the heavy particles. So the heavy particles, they go straight on this diagonal of my table. So the coarse, the heavy particles, they don't cross over the rifles. They move around those. Okay? And the fine particles, they do are carried by water and they move into the rifles. And that's how the separation is going to be performed. Okay. So moving on to another set of machines, and this is actually a set of machines. There's a family. It's a huge family of machines. I'm going to show you guys just like in general how jig concentrator works, and this is just one of many, as I mentioned to you. Okay, but how those guys work? We're gonna try to do something that we have on the sea. Okay, so on the sea we have waves, and when we have a wave, we have like a pulse, and the water is pulsing. And by pulsing, I have some mechanisms that's going to happen, and it's going to allow me to go with the pulse, separating heavy from light particles. And by doing this pulse, again, the heavy particles are going to be pushed down, and the light particles are going to be pushed up with the water flow, and then I can separate those. Okay, so in this case, again, there are many different variations for this kind of machine. I'm going to use in a piston. The other one I was using diaphragms, and we have many differences between those. Even I can use compressed air and things like that. But I have a screen over here, and those screens have the function to retain some material, and in some case I can even put steel balls on there to increase this effect, but has to make the particles life a little bit harder. Okay, and then the heavy particle is going to be able to go through the sieve and go out to the screen, and the fine particle is going to overflow with the water and takes a different way. Okay, so this is on short version how jigs work. Okay, so in this case, in this picture, you can see if you have the bed without being disturbed, you're gonna see this a range of particles that is completely random. Okay, that's not a problem at all with that. But when you start your pulsation, when you start your pulse, then you can see that the particles are going to be going into some sort of order. Okay, they're going to move, and they're going to move in an orderly way. So when you go to the pulsation and you have the hindered settling and go back to the pulsation, the dilatation of the bed and then the contraction, in the end you have these particles like this. So we have, even online you can see like U-shaped jigs. The guy started with something like this. So the pulsation enters in this side, okay, and in this other side you have the chamber of the jig. And there are quite beautiful videos about this, and the guy just put particles over there, like completely mixed particles. And one of the best videos that I saw was using plastics. Okay, so the guy had like 3 or 4 colors, different colors for plastics, and the plastics have, of course, different densities. And then they start pulsing the jig. And after a few moments, just moments, you can see that the plastics are all separating. Okay, and then you can see stratification of the plastics. Okay, and that's how jig works, and it really works. Okay, and you can use jigs for many minerals, including gems, and even for coal. Okay, for coal concentration, jigs are very good as gravitic separators. So again, another video from JXSC, and many thanks for the guys for this, okay, for producing those videos. And as you can see, they are a little bit different from the jig that I show you guys, but the idea, the concept was the same, okay? So you have the heavy minerals going down. You have also a bed composed by other material, and you have to use this bed in order to make your flow uh, going according your plan and to making some of the particles present in your slurry life a little bit harder. And then you have your overflow of material in the end of the jig. Okay, so it's quite important to have the feed on one side and the overflow on the other side. Okay, so in here it is showing you how they manage to form the pulse, and the pulse system, it's one thing paramount importance for the jig. And sometimes you just connect your jig to the water supply and use a piston, as I showed you before. And then what's happened is quite funny, because the piston starts to go up and down, and then the water starts to go up and down inside of your tubes also, okay, inside of your pipes. And then you take a look at your water supply, your water box, and the water box like blue, 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 because water is going up and down all the time. And I was doing this on my lab once, and then the pipes start to come out of the wall because of the vibration. And it was terrible. So that's why I told you guys that our walls are all repainted in minerals, okay? And I was telling you the truth. I mean what I'm telling you. Last not least, centrifuge and centrifuge concentrators. So if you go to artisanal mines in Brazil, I'm talking about gold, you're gonna see this. Guys love this. So in the beginning, and eventually even nowadays, you're gonna see people using mercury, okay? And yes, they take a small gold concentrate or pre-concentrate, and they prepare this amalgam between mercury and gold. And we know the problems, we know how the environment is going to be impacted, but we know this. They don't, okay? They don't know how to do this differently. And that's why they keep doing it. And we need to have a better argument with them. But then again, we're in university. We can't do this only by ourselves. But the idea was to take the guys from the artisanal mines, put this in our lab, and said, okay, you do your way, I do my way. Let's see who's going to profit more. Okay, and I would like to do this challenge. I really do. Okay, so if you're an artisanal mine and you want to be challenged, please contact me later. I would love to have you, to host you in my lab. And then you're gonna do this your way, I'm gonna do this my way, and we're gonna see who produces more gold in the end of the process with less money. Okay, and I think I'm gonna win. I definitely think I'm gonna win. Okay, so how this is a centrifuge works? Okay, this video shows you this. This is actually a quite new model of centrifuge. Okay, but you're gonna have a pot, okay, an area inside of your equipment, and you're gonna spin it. Okay, you're gonna spin it as fast as you can. And by spinning this, that's why it's a centrifuge. It's going to be like your wash machine, okay? And all the water in your wash machine has to go out because you have this drum rotated with your clothes inside of it. But in this case, I don't want the water go through the drum. I want the water going up to the drum. And that's exactly what's going to happen. So these lines that you can see over here, they are called rings. So I'm going to put rings inside of the material. I'm going to spin this around, and my particles are going to be thrown to the outer part. Okay, and then the rings are there to collect the gold, the heavy minerals, and they're going to remain these heavy minerals over. But the water is keep coming in, so the water has to go out, and it's go out on the top. It's going to overflow. Okay, and it overflows, carrying with the water all the light particles. So it works like a charm. Okay, and after some time, depending on what centrifuge are you using, the main tool that we have, but we're not limited only to these two models, are Falcon concentrator, Falcon centrifuge concentrator, and also Nelson concentrator. Okay, if you're using a Nelson concentrator, then you have to discharge your material. So you have to stop the concentrator, stop feeding it, and then you have to clean it. So it's quite common in Brazil. If you take a look at the gold circuit, flow sheet, you're gonna see that in the closed circuit that you have with the milling, if you don't put any kind of concentration in your circular load, what is gonna happen is the gold is gonna be retained in that circuit. Why? Because the gold goes into the mill. You definitely can't break gold in a ball mill. You're gonna only to produce like cigarettes of gold, and this gold particles go straight to the hydrocyclone. And the hydrocyclone is gonna look at it and say, "Oh, that's heavy." Okay, if that's heavy, it's because it's big. Okay, so it's a coarse particle. Goes down. Okay, you go to my underflow, and the underflow goes back to the mill. Okay, so the hydrocyclone can take a look at the particle and say, okay, that's because you have a specific mass, something like 18 grams per cubic centimeter. So you can go. He's not going to understand this. You just go and send the particles back to the mill. And that's why if you don't have any equipment to tackle with this, when you stop your mill and goes inside to change the liners, you're gonna be mesmerized with gold all around the mill. The mill is almost covered in gold, okay? And this actually happens. Even if you're working with something like 1 gram per ton or 0.8 gram per ton, after 1 year, 6 months, you have a very, very rich mill, okay? And that's not something that you want to have, okay? So we put this equipment, and after a few hours, like 8 hours shift, you stop your Nelson concentrator and you go there to clean it. At the beginning, you have to clean it yourself. Nowadays, they have a cleaning circuit. You don't need to go there. That's what we're going to see. Okay, you're going to take a look and you're going to see these black minerals that are probably magnetite. And also, when I say magnetite, you have to consider this. You can have gold on sulfates, and with the time, geological time, the sulfate can be altered into iron oxide. Okay, so you have a movement of removing the sulfur, and the oxygen goes in, replacing the sulfur, and that's why you have these blackish minerals. And people say, "Oh, this is hematite." That's not actually real hematite, but eventually you can actually have hematite, and even this hematite can respond to magnetic fields and things like that. So this is standard. Okay, you can have this in many places around the world, and then you can see your gold. Why? Because you have these two heavy minerals together, okay, and it's quite difficult to separate them. If you have pyrite, for example, the pyrite is going to be there also. And that's the Falcon concentrator. Okay? And this case is exactly what I mean to you. So we're near the mills, and we're taking part of the material that is circulating around the mill, and we not do this with 100% of the material. We just bypass something like 10 up to 30%, and then we feed the Falcon separator. And as you can see in here, we have a spiral over here, and from the spiral we have the Falcon. So yeah, these guys are taking a look. Those are also spirals in here and here. They are considering gravitic separation for this ore. Okay, so this is the Nelson concentrator. So I'm showing you Falcon and also Nelson. By looking by the outside, you can see the difference, but those are the two major companies, and they can manufacture for lab scale and up to very big industrial scale. Okay? They have machines for everything. And this is a view, okay, of this concentrator. And as you can see, you have this rotating bowl over here. It's quite important that you understand that we have to add more water. So those lines over here, it's water going in, and that's why it's called this perforation over there. You have to add water, and you have also the rings. And I'm gonna try to just color two of those. Those are the rings, okay? So the concentrate rings are here, better represented in yellow, okay? This is where the tailings is going. So the tailings go to overflow and leave the machine right over here. And it's a simple machine. You just have to rotate this drum, okay? And in the end, what you have is a fluid bed. Okay? You have a fluid bed. You can fluidize your slurry, and then the slurry freely flows out of the machine, and then you can separate minerals. Why this equipment is so nice? because since you're centrifuging your minerals, you can increase the difference in the density of those minerals. Okay, and that's why the machine works so nicely. Okay, talking about dense and density, we come back to our last group of machines that works with physical separation would be the dense medium separators. So what we have done up so far, we have take a look of different ways to separate, to sort minerals, and then one of those would be density or gravitic mass, okay, specific mass, so on. But density, it's one of those. Then we try to do what? To take the material and to accelerate the material. One way or another, just accelerate my particles. And by doing this acceleration, I could separate those. But then people had another idea. How about to accelerate this material over 1G? And then we have the centrifuges. And there are many ideas for centrifuges, including hydrocyclones, okay? Including cyclones. And that's a different chapter. But now let's take a look at a different way. So instead of increasing the specific gravity of these two mineral particles, why not change the medium? Why not change the water? So instead of tackling the particles, let's deal with the liquid phase, okay? Because if I have a liquid phase like this, with density around 2.8, for example, okay? If I add my minerals, and my minerals in this case are quartz and gold. Again, quite simple to have this association in Brazil in some places, okay? Quartz and gold and biotite. When I put this sort of mica, okay, mica, quartz, and gold. When I put this in this kind of assembly, what's going to happen is the mica is going to float, okay, the quartz is going to float because specific mass of quartz is around 2.65, and gold is going to sink. Immediately, gold is going to sink. And we can actually use this in our lab, and we do it in order to produce some curves that's going to, in the end, evaluate the liberation of gold in our material. Because if I have gold associated with quartz, then we're gonna see quartz particles sinking, okay? Then what we do is we increase a little bit the density of the media, and we try it again. And we're gonna see that those particles are not sinking anymore, or at least not all of them. And I remove the floated material again, and I'm gonna do this until I can concentrate only gold in one fraction and the other minerals in the other, and then I perform the graphics and I can evaluate the specific mass. So before you guys get this doubt, how can I increase the specific mass? It's actually the opposite. I only decrease the specific mass. So in this picture on your right hand side, you're seeing something real. That's something that we do in our lab. This picture is not from our lab, but this is made on a Brazilian lab. So you took, for example, bromoformium or Clerici solution, and you put this Clerici solution. Clerici is quite nice, but it's really expensive and toxic. And that's why we moved away from these inorganic liquids many years ago. We don't do this industrially speaking. We only do this in our labs, in a security facility on our labs. But nevertheless, as you can see over here, they are all toxic and really toxic. So if the people from Artesian Minds get to know this, they're probably going to love this because they love toxic stuff. I'm kidding, but they use toxic stuff. What we do here is we took our material, our liquids, our dense medium, and then we took it with the highest density that we can. Okay, so straight from the bottle, we just put it, and here we have it. And then we add our minerals. And then we're going to see that a lot of minerals, lots and lots of minerals are going to float, and a few are going to sink. Okay, what I do is I remove the material that actually sank. Okay, and then I add some kind of dispersant agent, and they're going to actually react. And then I slow down. I have to make a dilution of the heavy media. And one thing that is quite nice is in the end of the process, I have more liquid phase than I had in the beginning, of course, because I diluted it. But then I can just boil it up. And by doing this, I'm going to separate the diluent from the dense media, and then I just recycle the dense media. Okay, I can do this many times without any kind of degradation. But nevertheless, we can't do this industrially. It just doesn't work. And if you take a look at this is a picture from Albania, and they are working with chromite. And I was in one of those facilities. I actually could attend a conference in Albania, and I could see in the same day, in the morning, this plant exactly like this, using dense medium separation for chromite, and in the afternoon only gravitic separation. I know that both are gravitic separation, but I was talking about shaking tables and spirals and so on. So old tech versus new tech, and the guys were quite mad with each other because I was the only one in this technical visit that actually didn't manufacture equipment. So we're a team of 5 people, and 2 were from one company and the other 2 from another company. So they are in a huge dispute. What solution were better for chromite? And they were giving me those all great information. I was thankful for this. And Mohammed, here is my thank you also for you and for your hospitality. But in the end, they were preaching to the wrong person because I wasn't buying equipment at the time, and they were like gladiators. And mine is better, and no, mine is better because you're bad in this, this, and that. I said, okay. But one thing that you have to consider is when you talk about dense medium, I don't have only water. Okay, so I can use Clarice solution, yes, but not industrially. Why? Because it's expensive, extremely expensive, and is toxic. So what I'm going to use is I'm going to try to add something in my water. And by doing this, I'm going to increase the density of my water. I can do this with salt, and I can produce brine. Okay, and in some places we definitely use brine for concentration because we have lots of brine. And in other places we just don't have brine. Okay, so what are we going to introduce? And that's why we choose an alloy. We use iron silicium alloy. Okay, and this ferrosilicium alloy, it's one of the main dense media that we use. Okay, and it's going to sound strange to you, but I want to show you this video. I was impressed with this video, and it's about recycling. Okay, and this is happening on this company, the REM or REM, and they are showing you that they have many kinds of material to tackle with, and they're going to shaking tables. Take a look, trommels, and they have dense medium. Guys, it's what do we do? HPGR, crash the material, okay? Any kind of material. And then after comminution comes what? They wash the material, okay? And then they perform some kind of sorting, okay? So we can have some sorting, okay? And after, chemicals, okay? We have to add chemicals because we're talking about recycling. And take a look at this. They put 1.4 kilograms per liter, and then they have dense media separation because they are using that iron silicon alloy that I mentioned to you. But they are also using what? Plastics. They're using plastics and copper and things like that. It's extremely easy to make this kind of concentration, okay? So heavy media or dense media separation, it's quite interesting. And now they are increase more the dosage, and then they can tackle the metals, and they can separate metals from each other, okay? And that's why the video is showing to you. And take a look at this. You can even increase a little bit more your density. But if you try to do this, you're gonna sacrifice viscosity, okay? And you have to be extra careful in having the right viscosity. So in my opinion, we were talking about, or Ramon and I in the beginning, about mining and how mining is happening in some countries. I think Germany is going to be one of the first countries that are going to change from mineral processing direct to recycling process. And they are already doing this, okay? They are already having undergraduation courses, okay, on recycling. And I would not be surprised if this advanced design of recycling machines is this ADREM are actually from Germany. I would not be surprised, okay? Because this picture that you see in here, It's actually regular in Germany. Okay, it's normal in Germany to have this kind of view. And I went to a company like this, as I mentioned to you, and it's really impressive what the guys were doing there. They have dismantling. Of course, you have to take a computer, for example, and dismantle it, a laptop, and sometimes you can find spare parts, good spare parts, by dismantling. And of course, you're gonna sell it. People want new parts or used parts eventually. So yeah, they do dismantling. But after that, it's all about machines. And I was impressed. The number of mineral processing machines becoming recycling machines. Okay. And I was even more impressed when I came into one specific machine called eddy current separator. And they looked at me and said, "This is 100% recycling machine." I said, "No, it's not. It is this eddy current separator, but you can use for minerals." "No, you can. You can use eddy current separator for minerals. You can, definitely you can, because it's electrostatic separation." Okay. But when you take a look at how good this guy is for recycling, it's impressive, because you just put on a belt your material, and in the end of the belt, what you have is plastic on one side, copper in the other side, and the rest of the material in the other side. It's really, really impressive, because you look at it and it's all dry, and you can just see the particles flowing through one side to the another, and just jumping on top of the other, and the particles rearrange themselves in order to concentrate. And it's literally very beautiful to see it work. And again, on TU Claustro, I could see this machine working. And I'm quite eager to start some recycling projects in Brazil. But unfortunately, I have to tell you that we don't do recycling as much as we should. Okay. And here in my city, we have the recyclable collections just once per week. Okay. And we do this. We have this garbage selected, clean it, and we put it outside. And we can even eventually take a look at the companies here in our city, but it's not like that. They don't have the machines, they're pretty much manual, and we're far away from having this. But maybe if our universities start to take a look at the recycling and produce people who knows how to recycle, okay, then maybe we can develop a new product line, okay? And why not? I show you guys, why not? iPhone is pleased to say to the world that they use recycled material. So that's the future, that's the way to do it, okay? I think all companies should have been doing this, to open their products and say, okay, you want to buy this pen? Okay, this pen is just 1% with recycled material. And they're gonna say, probably, I don't want it. I want that other one with 30% of recycled material. Oh, but it's 2% more expensive. Oh, I'm available to pay for it, because that guy is more environmentally correct than you are. And I'm a fan of Greta. Okay, I think she's completely right, and I cheers for that young lady, and I get my fingers crossed for her that she's going to grow up and be a better adult than I am. And yeah, that she's doing the right thing. She's fighting the good fight, so I'm gonna pay 2% more on that product, and I'm not gonna buy yours. Okay, and that's the way to do it. So as the video showed very briefly, we can put our dense media inside of a drum, and we can just rotate the drum, and what we're going to see is the plastics, the light minerals are going to stay on the top, the heavy ones are going to sink, and when they sink, I just remove it by the drum rotation. Okay, just like we do with a mill, but in this case I want the heavy particles go straight to the top and just felt in a shot, and I remove it. Okay, so we can have this in a single drum, okay, or I can have this in a double drum. And this double drum, I can even put more medium on the second part of the drum, and I can have something like tailings, like middlings, and also concentrate. And in Brazil, I know 2 applications for this, fluorite and also manganese. And I have been in one place in Minas Gerais, they produce manganese concentrate using this heavy media separator, but just 2 places in Brazil. And Brazil is huge. So why not people are using this? I don't know. Maybe they are scared, maybe they don't know the technology, but we don't use it. We simply don't use it. And it's a very beautiful machine, even for a Tesinio mine, because it's safe. It's completely safe. Okay. So this is another design from the same machine. It would be pretty much the same idea. I have the same dense media. Okay. The particles are fed on the right hand side and they left on the left hand side, and as you can see, the black particles are going to float because here we're talking about coal, okay, and the white particles are pyrite, so the pyrite is going to sink. And then what is seen over here is the bucket wheel, okay, and this bucket wheel are definitely spinning around, removing the sink particles, because otherwise it's going to accumulate in the end. So what we're seeing is this is a Tesca bath, okay? So that ring, that bucket that you're seeing, it's exactly this, okay? As you can see, the size is a very big machine, okay? So this is going to be immersed into that solution, that slurry, and then it's going to spin it around and going to remove the sink material, okay? So if you think that it's too big and not so good for you, you can go for a drill boy bath, and it's again the same idea, the same concept, but instead of having the bucket wheels on the vertical, I have an inclined one, and then I have a smaller machine, okay? But inside would be quite similar. And then we can go for hydrocyclones again, and then we have heavy medium or dense medium cyclones, okay? So this hydrocyclone over here, or this cyclone over here, is the same cyclone that we mentioned before. It's going to work the same way as you can see on this picture, but instead of having only minerals, I have minerals, plus dense medium. And it's quite strange, I know, because you want to increase the difference in gravity and density of your minerals. That's why you have centrifuge, okay? That's why you're spinning the material. But then again, if you have also a high density of the media, the result is even better. And that's why you have these two things together. You have the dense medium and you have also the centrifuge action taking place. And I know for sure that people in Australia, they are using this, they develop machines like this, and they had great results in the past, and they just stopped. Okay, you don't see many things coming out on the literature. We can see many papers from heavy medium or dense medium hydrocyclones, and I'm not sure why, but they quite abort the idea. And I think it's a great machine. And here I bring you 3 more machines. They are quite similar to the hydrocyclone, but they're not hydrocyclones at all. Okay, so let's start with the DWP, which stands for Dyna Whirling Pool. So if you saw something like this, DWP is this machine. So we put our feed in the center. Okay, the feed is going to spiral all over it, and the floated material is going to live in here. But in here we add more medium, heavy medium or dense medium with water, of course. So that's why we have these 2 flows in here. And the green flow is going to show you the sink material, the heavy material, and that's how the machine works. And if you attach it more than one, for example, if I attach 2 DWPs one to the another, then I have this 3 flow separator. And the name, I think, is quite clever because you actually have 3 flows. You have 1, 2, 3 flows out of the machine, okay? And they baptize the machine as 3 flow. What is the main difference between DWP and 3 flow? DWP works with just 1 density of the medium, okay? And the 3 flow, you can have 2 densities of your media in the same machine because you add in here a medium number 2, for example, less dense medium, and when you reach the second chamber, okay, you add more, and then you have a density in here that is going to be smaller than in here. So in here they call it 2, and in here you call 1. So 1 is greater than 2, okay, and it works. Could be the other way around. Yes, you could add only water in one, for example, and then you're going to decrease your density, your media density. And this is Larkin-Dems separator. It's going to be, again, quite similar. You feed on this side, you put the medium on the other side. You always feed your machine on one side and removes concentrate in the other side, okay? And you're thinking about coal, and your concentrate is the material that floats. And then you take the synced material over here. Well, guys, to summarize our lecture, what we can see, that is particle size affecting all of our process, okay? All of those. So if we start with sorting, we're talking about particles that's going to be higher, coarser than 1 centimeter, okay? That's sorting. So if you want to do something like 5 millimeters, you're in a bad situation, okay? Because you're gonna have like a bed of particles, more than one, and all on top of each other, and you just can't see the particles and you can't blow the particles correctly. So go for particles above 1 centimeter, okay? So then we're below this. We're something above 100 micrometers. So what can I do above 100 micrometers, but below 1 millimeter? You can do gravitic separation. Truly, you can do this, okay? You can do this conventional gravitic separation or the enhanced one. What is the enhanced one? In our case, just consider that we're talking about centrifuge or centrifugation techniques. And then if you go and tackle this kind of particles, something around 10 micrometers should be your bottom size, okay? But actually, it doesn't work like that. 10 micrometers is too small. Okay, I would recommend you to try to stop around 100 micrometers or 50 micrometers, okay? And people are going to disagree, I know, but every time that I try to do this, I end up having problems. Particles are just too fine. If you want to tackle dense media separation, and if you want to do this in drums, as I mentioned to you before, as I showed you before, then you have to go to coarse particles. For example, above 200 micrometers. If you went to hydrocyclones, dense media cyclones, then you can go down up to 20, 30 micrometers. I think it's safe to say that you're gonna have a good result, okay? Go into magnetic separation. You're gonna have to make a split between dry one and wet one. If you're gonna tackle your particles in the dry way, definitely you have to go to coarse particles. If you go to wet way, then you can take fine particles. And if you talk about low intensity, high intensity, or high gradient, okay, so if you go to low intensity, coarser particles. High intensity, you can do this in smaller particles, okay, as the graphic is showing to you. Electrostatic separation, only coarse fractions, okay? In here, it's almost kissing 100 micrometers. Don't go 100. Don't go down to 100. You're gonna have problems. And then enters flotation. And the author in here, and it's Wills, and I know Finch also, okay? And Finch is a master in flotation, and they put flotation to 1 micrometer. It's quite difficult to perform flotation in 1 micrometer. I'm not going to say impossible, because it's possible, but it's not feasible. It's like this: it's doable, but it's not feasible. Okay, but up to 10 micrometers, okay, you can do this. We do niobium flotation 10 micrometers. Okay, you can do this. 20 micrometers, yes, standard. From 20 up to 200, we can do this. But 500 micrometers is too coarse, okay? Oh, but we can try to do this in this or that material. Yes, you can floated coal on 500 micrometers, but coal is coal. Coal is light, okay? So your bubble doesn't have problem to transport. Oh, Professor, you're talking about flotation, but I don't know what is flotation. So that's just a snake view from what is going to happen in our next lecture, because it's going to be all about flotation, okay? So we have to talk plenty about flotation, and then I'm finishing my part of the lectures. That's going to be me speaking speaking to you, and now we're going to enter at that seminars. And seminars we're going to talk a little bit later, okay? But nevertheless, take a look first on the particle size distribution. So if you want my opinion, I always do things like this. If I receive a sample, a mineral sample, just now, arrive a mineral sample to me, I'm going to take a look at the particle size distribution. Okay, and it's quite common that guys send us, people send us coarse particles because they just went there on the deposit and collect those. And we have, for example, right now, tin samples, we have titanium samples, and we have, the thing is cassiterite. We have gold samples, rare earth samples, and the gold samples, for example, that arrived to us, they are quite coarse. Okay, so the first thing that I did was to grind it using a jaw crusher. Okay? And this is quite nice project because it's a bilateral cooperation between two universities. We're working together in this material. And my colleagues from this other university send the material to us, and we start to prepare, then we're going to send them the material back, okay? And when we receive this material, we pass it through the jaw crusher. It was quite easy to break the material. I was even surprised, and then I took a look at the material. And just by looking, you can't see anything because the fine particles are all around the coarse particles, everything is dirty. You can't see much, okay? Then I went to sieving. I love to sieve material, okay? And if there's something that I do a lot in my lab, it's sieving. Okay? So I went to the sieving, wet sieving, and I sieve like 5 kilograms of the material. And I did this coarse fraction and also small fraction. And in the end, I could see the material shining to me because I could see the wet material and completely clean. And we could see a lot of sulfates, and they are very, very beautiful sulfates. And just by looking, we can say that it's cyanopyrite, pyrite, and even some small amount of chalcopyrite. And then we have material to go to SEM, because SEM and EDS, they are way better for some materials than optical microscopy, okay? Because I can just take a look and shoot it, and I have the chemical composition of just one point of our material. And that's what we're going to do. And after that, we can also send the material to XRD. And since we have like 2 minerals only association, because we can take a look at it and say, okay, there is just 2 minerals in here, or looks like it's just 2 minerals, we expect to have a great result from the XRD. Because when you take a look at the graphic, the spectrum of the XRD, if you have plenty minerals, you end up not being able to see anything. And if you have a lot of quartz, then you take a look and you only see quartz, okay? But if you can actually sort your minerals, oh, I'm going to take this one and there is no sulfites on this one. Yes, it's pure gangue mineral. So let's analyze the gangue, okay? And that's something that people actually doesn't want to do. They think that you have gangue and that this is it, it's gangue. But I have to find a property that allows me to separate the minerals that I want, the ore from the gangue, okay? And that's why I have to take care of the gangue. I have to look at the gangue. If I don't know what is the gangue, I don't know how to separate the minerals. And then we go to chemical analysis. It could be XRF, fluorescence. It could be ICP. It doesn't matter. You just go to the chemical. And when you have the chemicals and when you have the crystalline structure and when you have the pictures and that allows you to see morphology, then you start to finish this jiggy puzzle. Okay? Then you start to put the pieces together and said, okay, that's the particle size that gives me high liberation, and this particle size is too fine. And then I start to think, oh, it's possible to float this. Yes, we can try to use this or that chemical, and it's possible to float this material. So let's go for it. And now we have an idea. It sounds good to me. It sounds like a plan. But if you just take your material and feed your equipment and see what's going to come out of there, eventually you're not going to have anything. It's pointless. Don't do this. Okay? Go step by step. Oh, but it's going to take me a lot of time. Yes, it's going to take you a lot of time. Because it's going to take you something like 1-2 weeks for the first stage. That's sample preparation. Eventually even more, depending on how much is your minimum mass. to be representative from your deposit. And then you're gonna send samples to the chemical analyzer and so on. I already mentioned all the analysis. And it's gonna take you something like 30 days to get your results back. Okay, at least in Brazil right now, if you don't pay that rush fee they demand to you, they're gonna put you on the hold. It's gonna take you like 3 up to 4 weeks to get your results. And during this time, you can't stay idle. I know this, but go to other things. Go, for example, to milling tests. Go to measure WI. Go to see how your material is behaving in other equipment that you're gonna have to do this. But wait for a little bit for concentration. Okay, don't rush things. Take a look. Take a deep breath, and then come back. Okay, then you come back with your ideas. Okay, now I know better. Okay, now I have a broader vision of my situation. I have this ore, and the ore is composed by X minerals bearing my element, my interested element. Okay, so I have this X minerals, and my gang minerals are those. Okay, and what are the similarities? Oh, I have a mineral that has my element, my interested element, and also I have the same element that I have on the mineral, my gang mineral. For example, sulfates. I have sulfates bearing gold, and I have sulfates that doesn't have gold, it's sterile. How can I separate sulfates? By flotation? Probably not. Okay, so okay. So I'm gonna do this first stage, and I'm going to separate these two sulfates, and then I'm going to this stage and this stage and this stage. Okay, and the last thing that you consider, is metallurgy. Okay, so don't go straight to hydrometallurgy. Don't go straight to extractive metallurgy. Normally, when you do this, your chemical consumption is going to be too high. Your cost is going to be up to the roof, and you can definitely make a route out of that. Almost all the time, you can come back with a hydrometallurgical process or a pyrometallurgical process or an electrometallurgical process. So the metallurgicals, they are very clever. Okay, they break down your material to the atomic level, if you want. But then again, you come to them and said, how much is it going to cost? They say, is there a problem? Yes, that's the problem. So wait until you can. Okay. If you get to the bottom of everything that you know, then call the metallurgist and hand some samples to him. Okay, but not before you finish everything that you can do for mineral processing. Okay, that would be my best advice to you guys. Okay, try everything that you can, but try wisely. Okay, so think like this: you're going to cook, and you have only rice, and rice is staple carbohydrate for many people in the world. Okay, so rice is one thing that you can also see as common food, mainly people, a lot of people in the world. Okay, so you have rice and only rice, and you have to feed you and your family with rice, but you have some spices. Okay, and you can try to make rice with one of those spices, but you can also add all of the spice. If you take your rice and put at the same time all spice that you have, you're gonna have something in your hand that probably nobody's going to like it. You're just gonna throw your rice directly to the garbage. So do this. Understand what you have in your hands, and then start testing. Okay, I'm gonna try the first one, the second one. Now pair tests. I'm gonna try the first with the second, the first with the third, and so on. Okay, and guys, I know for sure that you can add plenty of stuff in your rice. Okay, and sometimes the results are quite good, sometimes not so good. Okay, but then again, that's the way to do research. Okay, so go to one machine, try to use it, got the results. Oh, they're not so good. I just got a very small enrichment. Yeah, but how much mass did you remove? Okay, so you have just small enrichment, but you have 100 tons, and in the end you have 50 tons. So that's good. Okay, that's good. Write this down. Moves to the next one, and so on. Okay, and then you come back with all of your data compiled, analyzed, statistically analyzed. Then you start to think, if I do this, I'm gonna get this. Okay, that's a good result. If I add that machine after this first one, what's gonna happen? And then you're gonna have a very good route in order to produce the mineral that you want. Okay, so guys, we're going to finish right now. I hope that's okay to you, because that's all for physical separation. Again, if you take Will's book or other book, you're gonna see plenty of more pages on the subject. This is just brief information, but I think it's possible to give you guys an idea on how important and how deep is mineral concentration. Okay, for next Tuesday, we're gonna face flotation. We're going to try to understand a little bit how flotation is performed, what kind of equipments we need, and what we will be able to do. And it's definitely beautiful technique and a young technique. Okay, just 100 years old. Okay, it's quite young technique for mineral process, and that's why we're just scratching the surface of it. Okay, so guys, thank you so much, and if you have any questions, I'm pleased to answer those. Okay, no questions. So thank you very much, Ramon, Barbara, Nilo, Mateus. Oh, I'm seeing Mateus today. Hi, Mateus. How are you doing? And Santiago, and also Gisilene. Okay. Oh, Ramon.
A moment.
Feel free to ask
A
your
moment.
questions.
Okay.
Oh, just saying bye.
Let me talk. Huh?
Sorry. Just a minute. Can you repeat, please? I was muted.
Okay. What you was explaining about the processing, and I want a little bit talk about the way we talk the garimpo.
Yes, artisanal
Processing
mines.
Yes.
Yeah.
Processing gold. So what mostly nowadays they have the crusher. Not we call it crusher, but it's a hammer mill, sluicing. A lot of mercury. So if you want, like in Suriname, there's a lot of tailing material of this, and if you want to reprocess it or process it better, because there's only one stage, the sluicing. It can go like you said. You take you collect the samples and then you characterize the samples.
Correct. The first stage is always characterization.
Okay, but if I go and I put a jig and a concentrator to see, what can I capture, and in the meantime, the same samples I go for graphite recoverable gold for more grinding, because I want to see how far there are a lot of mixed particles, and then go through to analyze and things like that, and then maybe you can adjust your centrifuge, your or increase, like you said, magnetic separation, because after the hammer, well, they have problem with magnetic for the iron slate, the slatation of the hammer, and then when they treat it, it becomes like black gold, because of magnetic and the iron, the pieces of iron.
Yes.
And so, so some kinds they use a hand magnet to separate this part. But in in Suriname, there is a lot of tailing of this material. So we have another problem that the Chinese is introduced. Not they don't call it cyanide. They call it jinjiangmar, but it is like cyanide. So they rush to they want to they go to the tailing, and then they concentrate gold. My question is, if I can treat the tailing, and then in the same time study the tailing, with the hope that when I treat it, because of particle, there's still gold particle liberated after the sluicing, and then I hope I have to catch that one, and then when I go to characterize, and then I concentrate, I regrind, and I concentrate the tailing again. What about that?
Yeah, what I can tell you about gold, Ramon, the first thing that when you talk about gold that you have to have clear in your mind is, where is the gold? Okay, it's a simple question, but it's a quite profound question. Okay, because gold can be atomically distributed inside of crystalline structure of all other minerals. Okay, so when you take the mineral, it's just like this. You take the rock. Let me take one here. I take this granite, and when I look to this granite, I'm gonna see sulfides. Okay, it's not the case. It's not a granite with sulfides on it, but let's consider if it is. So I can see spots of sulfides, and when I start to analyze the sulfides, I can find gold. I can find gold. I said, but I can't see gold because I took rocks, chunks of this, and I grind this, I mill this, and then the gold shows up. So where is the gold? So that's why when you start to make an MLA analysis of this kind of material bearing gold, sometimes you end up making like 100 thin sections, and you find one particle of gold. One. Okay? And you gotta be lucky to find one, because you're searching for a needle in a haystack. You have to remember, Ramon, it's 1 gram in 1 ton. Okay, so I have 1 ton delivered to me, and actually I have 1 gram of gold. And that is something funny. Okay, I was working in a university, and then one of my students came to me and said, "Oh, professor, are these the gold samples that we're supposed to receive?" And I told him, "Yes, that's the ones." And there was a guy performing some maintenance in our lab. Okay, and then I came back, and the guy was trying to steal the bags. Okay, the sample bags. And I came to him and said, "Oh, my friend, don't worry, it's less than 1 gram per ton. So if you took everything that is in here, everything, it's less than what I have in this ring. So if you're gonna steal something, steal my ring, and you're gonna be richer than all of this. It's 18 carats ring, so plenty more gold in here." And he looked at me and said, "Oh, no, I'm not going to steal from you." Yeah, okay. I saw you try to carry the bags, but there is nothing there. Literally, there is nothing. So if you don't process huge amounts of material, you don't have gold at all. Okay. So go to characterization. Okay. And what happened to me last year, we had a project running in collaboration with another professors about gold characterization. And we took samples from an area that has been mined over 200 years here in Goiás. So from time to time, people go there and try to excavate and try to find gold. and everything that was there easily to catch, it's already been catched. Okay, so they call this area like fine gold, and if you go work there, you should prepare to see fine gold. And then I knew that they had gold, and I can show you guys some pictures next lecture, okay? Because we end up making flotation of this material, so I can add some pictures about this. I will do this, okay? I'm gonna show you some pictures. And then when I was sieving the material, I was seeing something floating, and it looked strange to me because it was glitter floating. And I thought to myself, maybe I'm losing gold, because you have hydrophobic gold, Ramon. Look how amazing it is. Your particles have density around 18 and they are naturally hydrophobic. So I went there, collect those material floating, okay, and send them to optical microscope. And when I sit down on my microscope and look to the material, bang, gold particles. And then I have to change completely my procedure for performing the sieving, because I was losing all the gold. Okay, and then I send the material to SEM and EDS, and I got beautiful gold pictures. And I showed this to some geologists, friends of mine, and they look at this, how you was managed to get there? I said, yeah, sieving. I just sieved the material and I got this. But this is impossible. No, it's not impossible, because I have a pre-concentration of the gold and perform the sieving, and there it is. In the end of the day, we could make a mass balance. And next lecture, you guys are going to know about mass balance, okay? And you have to know how to calculate this. So that's part of our next lecture. And when I performed the mass balance, I was able to prove that the actual route they have nowadays, using centrifuge, using just this centrifuge as a main concentrator, only recovers 25% of the gold. 25. 75% of the gold goes straight to the tailings. Okay. So when we collect samples from the tailing dams and from the mine, the grade is the same. It's like one gram per ton. It's just like they take the ore, they took a little bit of the gold, and they just put it back. The same grade, 1 gram per ton. But we're making money, we're profiting, yes, but you're putting back the same ore in the environment. And then we went to flotation. And in flotation, we could take 1 gram per ton and increase to 13 grams per ton with just one stage. And we didn't try any other test or any other equipment, because as I mentioned to you, I went there and I saw what was the particle size distribution, what was the mineral liberation, who cares gold and why, and then we were choosing. Okay, this is flotation. There's no other equipment that we should do. It's just flotation, and we solved the problem using flotation. Okay, but then again, if you consider flotation, you have to think about what's coming after flotation, because you don't perform iron ore flotation just to have iron ore. You want to sell this, and then you have pyrometallurgy. But if you have flotation for gold, then you have probably a CIP, carbon in pulp or carbon in leaching stage. So you have cyanide. Okay, so you have to replace mercury to cyanide. And sometimes people come to us and said, I don't want to do anything with cyanide because I don't have environment license for cyanide. So don't even bother to try flotation, okay? Because if I have to go through flotation, it's pointless for me. I can't process this material. And that's something that you have also to consider, okay? What you can do is limited. And what your client or your partner can do also is also limited. Okay, so sometimes you have a best solution but doesn't apply. Okay, for example, I come to Namibia and tell the guys, okay, let's put something here in flotation in there. I said, oh, we don't have water. Okay, and you don't have flotation. So you have to consider all of this. Okay, so in order to choose First thing is you need some kind of file about the ore. Understand the ore. Okay. If you're not good in this, in characterization, find yourself a geologist, your best friend from now on, and you ask him to help you. But the problem with the geologists regarding this is they love rocks, they love minerals, and we grind minerals. Okay, we don't have this same feeling about them. They like to take this and to put in as samples and to keep forever, and we just crush them. Okay, and you separate them. So you have to be extra careful. And this is just a joke. Okay, I have many geologists as friends, and the joke is you have to talk to them and explain to them exactly what you want, what kind of information you want, because sometimes they produce documents this big, and I read through it all, and in the end I come and I have zero information that's going to help me to process the material. Zero information. And I have to do my own research, and then I have data that I want, and then I can go and perform some tests. Okay, and it's quite regular. If you take, for example, a PhD thesis of a geologist, it's going to be this big. And if you read everything, you have geochronology, you have rocks association, you have where the gold is, like which basins it is, when it was formed, by what process, everything. You know everything about this. It's just like it's a CSI operation. Okay, the guys go there and they have all the information, and then you ask him how you're going to recover the gold. I have no idea. I don't work with this. I know where is the gold, what's the name of the rocks and everything, but how to recover the gold, I have no idea. It's good information, but for me, it's just data. It's not information. It's just data. Oh, this deposit have X amount of million years. What I'm going to do with this? No information. But for example, if they come to me and said, "Oh, this is an igneous deposit, and this is a sedimentary deposit," and I work with phosphate rock, that's data. That's data. Okay, that's important to me. If they come to me and said, "Oh, you have in here, okay, mica, and in here you have silicates," that's information. Okay, that's good for me. Okay, and if he gave me the right answers, then he can show me the way to do it. But if they give me the wrong information, there's nothing that I can do at all. And you have to be careful with the second thing about geologists, how they collect samples. Okay, it's completely different from how I collect samples or how we should collect samples. Okay, so I'm not saying wrong, I'm saying just different, because sometimes the geologist, he's walking through the field, okay, and he sees something and he said, "Okay, I'm going to collect a sample of this rock," and it's okay, but he just took a little bit of that rock and he's going to analyze that rock. But when I arrived with a big machine and I took everything around that rock. So I have to know the rock and everything around it in order to make it feasible. Because when I feed my mill, I'm gonna feed with everything. Okay, so you have to go with the geologist into the field, and you're gonna tell him, "Okay, you're gonna take this, but now you take this, this, and this." I said, "Oh, why? That's pointless. We don't want this rock." Yes, we do. Yes, we do. Okay? And they know this, because when they come back to the field, they start to make different sample collections. They're going to use different approaches and so on. But that's the good geologist. Okay, that's the kind of geologist that he knows or she knows that in the end of the day, this material is going to feed the mineral processing plant. Okay, and if your friend, if your geologist have this idea of how things works, then it's a good acquisition for your team. Okay, but the first thing, understand the ore. That's the first advice. Okay, if you want, we can talk about this for hours, but the first thing is understand the ore. Only after that, move away. Let me just give you one last example. Okay, titanium. For many years, people only produced titanium from rutile. If titanium was in ilmenite, it's a waste of time because it's not going to be feasible. The process is going to be very expensive, so pointless. And then some guy called Daniel Goldman in Germany, he developed a route that he can, by hydrometallurgy, recover titanium in a feasible way out of ilmenite. Look how game changer this is. So now you add hydrogen in your mill, and you start to changing your minerals in order to produce, in the end of the day, titanium. Okay. So what are we doing right now? We're taking a look at ilmenite. But if your ilmenite has manganese as contamination, the process doesn't work. So at the beginning, you just take a look at the mineral and said, ilmenite, I don't want it. I just want rutil. Nowadays, I look and said, okay, you have a blend of ilmenite and rutil. Oh, I want it. Okay, let me see. When I take a look at deeper look, I said, but you have manganese. I don't want it to throw it away. Okay, so yeah, just consider quartz for PV, photovoltaic panel. If you have something like 5 ppm of iron, it's bad silicon. You can't use that quartz. So again, you have to take a look at the ore. The first thing is understand the ore. If you have a good understanding, a deep understanding of your ore, maybe you can choose the right route, okay? Or maybe you're gonna end up like me, with testing everything that we have in our hands, all our weapons, in order to try to concentrate rare earth and fail one after the other. Can't happen.
Okay. Thanks.
Not at all. Yeah, it's a pity that we don't have more time. If we had more time, more lectures, then we could enter into mineral characterization. Okay, and mineral characterization is not only about chemical or crystalline structure. It's also about technical characterization. So performing tests on the lab, but mineral processing tests. And in Brazil right now, that's also some challenging for us because we don't have many facilities that you can go and test your ore. We have CETEM and more a few 4 or 5 places that you can actually go there and run your ore. So this is a challenge in Brazil. We need more companies that can perform mineral processing on lab scale if you just deliver the samples. Okay, but doing this in the right way, in a wise way, and in order to solve problems. It's all about solving problems. Okay, guys, thank you very much for attending my lecture today, and I see you guys on next Tuesday. Okay, bye-bye.